So let's start with material. Hopefully finish up material today. Maybe we'll have to finish up a little bit tomorrow. And then done with material for calculus. Wow. Wow. Time flies when you're having fun.
That's right.
All right. So I decided I'm going to try and follow the book as best I can. That way you can reference the book as much as you can. But I'm going to do a bunch of prep work to set up for where the book takes over.
Okay.
So none of this is in the book.
Okay.
In this column right here. Book starts in this column right here, kind of. Okay. So reminding ourselves of exponentials. Exponentials. A number to some power. Exponent. When you apply exponents to something. That's what I mean by an exponential. Let's go over some basic exponent properties. A to the power of 0, any number to the power of 0 is always 1. Remember that? Old algebra rule. With the exception of 0 to the 0. Sometimes people define it as 1. We won't get into why. Next, a to the power of 1 is always just a. Make sense? That's what I mean. And then if I have a to the x times a to the y, that's the same thing as a to the x plus y.
Okay.
So a quick example there, that one should make good intuitive sense, but let's just make sure, for sure it makes sense. If I have 2 squared times 2 cubed, what does that mean? What does 2 squared mean? It means I have 2 times 2, 2 times, right? This is equal to 2 times 2, and then this one is 2 times 2 times 2, right?
Mm-hmm.
And how many 2's do I have when it's all said and done?
5.
You just add them together. That's why you just add exponents. Make good intuitive sense?
Yeah.
Reminding you of stuff that you should be quite familiar with, but I know after a while we lose track of what the rules are, what we can and can't do. Basic tests with simple algebra will remind you what the rules are and why they make sense. Let's look at the next one. A to the x to the y. Imagine I had 2 to the 2 to the 3 now.
Okay.
And you can put the parentheses like that. 2 to the 2 to the 3. That means I have 2 to the 2 3 times. So this is equal to 2 to the 2 times 2 to the 2 times 2 to the 2. Right?
Mm-hmm. Yeah.
Which is equal to, now we know how to handle these, we just add up the exponents. 2 to the 6. Notice that's a product of 3 and 2.
Okay.
Because I need to add up 2's 3 times.
Gotcha.
Make perfect sense?
Mm-hmm.
Okay, now let's look at a to the x divided by a to the y, and why this divided by acts the same way as a negative exponent. So let's say I have something like 2 to the 5 over 2 to the 3.
Okay.
Now, one way we can think about that is we have 3 2's down here, cancels out with 3 2's up there, right?
Yeah.
And we're left with 2 to the 2.
Yeah.
Which is the same thing as 5 minus 3. The 3 canceled out with 5 of those 2, or this 3 gets rid of 3 of those 2's. Let me just make it stupid obvious in case for any reason it's not completely clear. Writing it completely out. That 2 cancels with that cancels with that cancels with that. We have 2 2's in the numerator. So it's the same thing as 2 to the 2. And subtract the exponents.
Okay.
So this is the same thing as 2 to the 5 minus 3.
Okay.
Okay? So there are our basic rules that we know we can use when we're dealing with exponents. Now we get to logarithms. The logarithm is the inverse function of the exponent. An exponential function, when I have something like x is equal to a to the y, this is a function in terms of y instead of in terms of x, but don't let that throw you off.
Okay.
This function, I give it an exponent and it spits out a product, right?
Yeah.
If I plug in 3 for, pretend a is 2, let's look at a concrete one. Let's look at y equals 2 to the x. I plug in an exponent, x, and it spits out a product.
Yeah.
The logarithm does the exact inverse. You give it a product and it spits out the corresponding exponent. Make sense?
Mm-hmm. Yeah.
Okay, so some really simple exercises to make sure it makes sense. What's log base 2 of 8? Or in other words, 2 to what power gives me 8? What's the exponent I apply the 2 to get 8?
3.
It's just 3.
Gotcha.
Make sense?
Mm-hmm.
Remember, I should always be able to rewrite it as 2 to the something. Whatever that something is up there is exactly what goes out here.
Okay.
Same thing. Make sense? All right, so what's log base pi of pi to the 5th?
Just 5.
Just 5. What's log base 3 of 81?
4.
4. Wonderful.
Okay.
So that's how a log function works. Here's the definition we're using in this class, not the definition you have to use this. Okay, so now let's look at some basic properties of logarithms, the same way that we had our basic properties of exponentials, of exponents. All right, log base a of 1 is equal to what?
1.
A to what exponent always gives me 1?
Oh, 0.
0.
Wow.
Log base a of 1 gives me 0. What's log base a of a give me?
That's
1. A to the 1 is a, or sorry, a to the 1 is a, however you want to think about it. Make sense? We'll come back to change of base, so I should have written that later. I'm just writing it as I have it written. Next. Remember, log takes in a product and spits out exponents. So the log of a product is equal to the sum of the logs. The log on the product is equal to the exponents this spits out is the sum of the exponents of this with the sum of the exponents of this.
Gotcha.
The exponents of x times y are equal to the exponents of x plus the exponents of y.
Okay.
Make sense?
Yeah.
We'll prove these ones, but I just want you to get intuition for them first. Okay? Well, let's just prove them as we go. Okay. So I'm trying to prove that log of x times y is equal to log of x times log of y. So I'm going to start with let n equal log base a of x and m equal log base a of y. You with me?
Yeah.
So I'm just naming whatever the log base a of x would be. It's got to be something. Okay, now notice this equation gives me what information? It tells me a to the n is equal to x. This is logically equivalent to writing x is equal to a to the n. This and this encode the exact same information.
Okay.
Similarly, this is telling me y is equal to a to the n. Good?
Mm-hmm.
Exact same information. Now what was I trying to show? I was trying to show that the log of x times y is equal to something. Let's see what this is equal to. Well, log base a, sorry. This is equal to log base a of x times y, which is equal to log base a, right? When I multiply terms, I add their exponents.
Mm-hmm.
And then we know, based off definition of log, that this is just n plus n, right? When I take the log, it spits out the exponents.
Yeah, gotcha.
Which is equal to, what is n? N is log base a of x. What is m? It's log base a of y. Follow that?
Mm-hmm.
There we go. All right, let's do the next proof. Let's see what our next proof is. So we're looking at log base a of x to some exponent k. We're going to prove that you can pull that exponent out in front of the product. Okay?
Mm-hmm.
How am I going to do this one? X to the k. Shouldn't have relied on my ability to do these on the fly. There's a simple way to think about this. If I say y is equal to log base k, then that's the same thing as a to the y is equal to x to the k. So what does that give me? So that gives me log base a of x to the k
Okay.
is equal to, now what does this equal? This equals just y.
Mm-hmm.
No, I'm still doing something weird. All right, we'll come back and play with that one. I don't want to go down. It's something really simple. I'm just not seeing it right now. I think if I come back at it in a second, it will be obvious to me what to do. Okay, let's do the next one real quick. Oh, this one falls for free from this one. So we'll have to prove those two together. Let's look at the next one. Log base a of x to the y of x over y is equal to the difference. That also means it. Well, sugar. Let me look this up really quick and get my feet off the ground. I don't know, tell me your internet's down. Well, alright, we won't dwell on it. I'll come back and figure those out. We'll come back to those. Let's pretend that we do have this one. Pretend that I did show this one to you. We'll come back and do it. I just don't want to sit here and start for a second. But it just says that if you have the log of something to some power, you can pull that power out in front of the log. So k times log base a of x. And then the next two fall from this for free. So the next one says that log of x to the negative 1 is the same thing as pulling that negative 1 out in front. It's just a special case.
Okay.
You see how this is a special case of that?
Yeah.
And then this is almost a special case of that. Let's look at this one real quick. Log base a of x over y is equal to, one way that we can rewrite this is log base a of x times y inverse. Right?
Mm-hmm. Okay.
Now we know that the log of a product is equal to the sum of the logs, so I can rewrite this as log of x plus log of y, that's a g, log of y inverse, right?
Mm-hmm.
And then I can pull that negative out front, which makes that a minus. So a log of a quotient is the difference of the logs,
Gotcha.
which we already know. When you take a log, if we look at the exponents of a quotient, we look at the difference of the exponents. Make perfect sense?
Mm-hmm.
And then change of base formula. This is the last one. This is a very useful one that we'll use a lot. Hopefully I don't get stuck on this one. So this is telling us how we can always rewrite a log in terms of a different base.
All right.
Make sense? Notice that log base a of x is equal to, maybe I don't want to work with base a. Maybe this base is 3 and I'd rather work with base 2.
Okay.
Make sense?
So it doesn't matter which base you choose?
That's what we're showing. We're showing that you can change the base. You just have to use this formula.
Okay.
So log base a of x is equal to log base, our new base, whatever base you wanted, b of x, pick any base there you want, over log base b of a.
Okay.
So log base a, we'll say y equals log base a of x. I don't know if I'll need to reference that. So this is logically equivalent to saying that x is equal to a to the y. So then log base b of x is equal to log base b of x is the same thing as a to the y. Right?
Mm-hmm.
Which is equal to, I know I can pull that y exponent out front. So y times log base b of a. You follow me?
Mm-hmm.
So notice log base b of x is equal to y times log base b of a.
Okay.
So I can say y is equal to log base b of x divided by log base b of a. And then what was y? It was log base a of x.
Yep.
So we can replace that with log base a of x. And there we go, change of base. Make sense?
Yeah.
Okay. So those are our basic log rules. Now, let's get to our basic definition of e. We talked a little bit about this last time, but let's reintroduce it. What is e? By definition, e. The same way what was pi, it was circumference divided by diameter. That's pi. It's not 3.14159. It's circumference divided by diameter for any circle. What is e? It's this limit. Now notice that this limit is kind of weird.
Yeah.
This function is a little weird. We have 1 plus t to the 1 over t, and we're doing it as t approaches 0. So if you wanted to get some approximation for t, what would you do? Plug in a really small number. Or sorry, if you want some approximation for e, what would you do? Plug in a really small number for this, and that would give you an approximation. Right? Because as this gets closer and closer to, as t gets closer and closer to 0, the whole thing gets closer and closer to e. So e would be close to what we would get if we plugged in like 1,000th, 1/1000th into that thing. What was 1 plus 1/1000th equal? That, right? Mm-hmm. And now we're saying that to the power of 1 over 1/1000th, or in other words, 1,000. The reciprocal of 1,000th is 1,000. And if you calculated this, so if you calculate 1.001 to the power of 1,000, then you get an approximation for e. And notice that you're almost doing 1 times 1 times 1 times 1 over and over again, so it changes very slowly. But if you did that 1,000 times, that growth is going to compound.
Okay.
Make sense?
Yeah.
And so, strangely enough, this thing approaches just one number. It doesn't grow to infinity. If I pick smaller and smaller numbers there, and making bigger and bigger numbers there, this thing doesn't grow to infinity. It just gets closer and closer to one number, namely e.
Okay.
Okay. So e, what is it roughly? It's roughly 2.71828 da 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 da. You can calculate it as well as you want. Make sense?
Okay. Yeah.
Okay, so now we're going to define a new symbol, and it's going to be basically all the logarithms that we use in this class going forward. We hardly ever take logs base 3, or logs base pi, or logs base 2, or logs base 10. That hardly ever happens when you're working in calculus and physics. You almost always want to work with logs base e of x.
Okay.
It's very, very useful. The same way measuring angles as radians rather than as degrees turned out to be really, really useful. This is a really, really useful base to have. And since we do log base e of x so much, we have a special name for this. Since this logarithm shows up so much, we call it the natural log. And we represent it with just ln. So ln x is the same thing as log base e of x.
What does that give you?
A shorthand way to write this.
But why does it pop up?
Why does e pop up everywhere?
Yeah.
Why are the laws of the universe the laws of the universe? It's just a fact of nature that e pops up everywhere. And we'll see it. But yeah, it pops up everywhere. Okay. And it's a very easy number to work with. You're about to find out. E is our favorite number to work with almost.
1 pi?
Well, when we're taking derivatives or calculating integrals. And you'll see why. It's wonderful. Okay. So, we're going to be using this natural log symbol almost exclusively. Sometimes we'll use log base something of some number. But almost exclusively, we'll be talking about natural logs for the rest of this class. And they will be the majority of the logs that show up when we do physics as well. Okay, so let's just play around using our log rules a little bit to see how we can rewrite these things. So I'm going to take natural log of 3x to the 4 over 2 times y squared. And I want to rewrite this, I want to split this up into a bunch of separate logarithms. And this is going to be something useful for calculating derivatives of logarithms. So teaching the rule real quick. I'm going to apply these rules to this and just rewrite this out as many simple logarithms as I can. You with me?
Mm-hmm.
Yeah.
So when we look at natural log of 3 times x to the 4th, why am I writing it just up there? Well, first rule, I can write this, we have this divided by this. So I can write it as the natural log of this minus the natural log of this, using my first rule. So I can rewrite that as 3x to the 4 minus natural log of 2 times y squared. You with me so far?
Yeah.
Yep.
Okay, now that's not all we can do. I can split this product of two numbers up into two logarithms. And I can split this product of two numbers up into the sum of two logs. So this is also equal to the natural log of 3 plus the natural log of x to the 4 minus, tell me now.
Natural log of 2 plus natural log of y to the 2.
What do you think, Jeremy?
I thought it was minus.
Minus. Remember, we're subtracting this whole log.
Oh,
And this plus this gives me that log, but I need to subtract this whole log. So you got to distribute that minus here. So either, if you want a plus there, then you need to use parentheses here. And then if you want to distribute the negative, either way is fine.
okay.
Make sense? That was the gotcha, the reason that we did this example. Okay, so that is minus minus. Now, last thing we can do is we can bring exponents out and bring it in front. So this is equal to natural log of 3 plus, bring the 4 out, 4 natural logs of x minus natural log of 2 minus 2 natural log of y. And I might start getting lazy and stop writing the parentheses everywhere. It's a function, you know it is. I'm not going to. Same way we get lazy with our trig functions.
Okay.
Okay? And then this is how we would write it out. And then if we need to work with it, like calculating a derivative or something like that, even though you're not sure how to do that yet, this is a much simpler thing to work with than this, or than this.
Okay.
Because natural log of 3, first off, that's just a constant, so if you're taking the derivative of that, you know that's a 0.
Oh.
Natural log of 2, that's just constant, so that's a 0. You don't know how to take the derivative of logarithms yet, but you know just apply the rule to that, just apply the rule to that, and then this we need to have another y prime on there if we're doing with respect to x. So it would be much easier to work with than this initial beast. That's commonly what we do when we have logarithms, so we split it up to calculate our derivatives.
Okay.
Common thing to do. There's no requirement, there's no you have to do this. Just one more thing to be aware of in case you got a problem that's really hairy to work with one way. So let's keep playing with these log rules and expanding other things out. All right, so let's start expanding this one out. Tell me what to write.
The natural log of x to the 2 plus 1 minus the natural log of root x.
Can we do more?
Yeah. The
What's
first
next?
one can be split up to 2 times the natural log of x plus the natural log of 1.
Does it work with addition?
No! That was the alarm, keep going. Stop what you're doing. The exponent of a sum is not equal to the sum of the exponents.
Okay?
The exponent of a product is equal to the sum of the exponents. There isn't a log rule here that says what we can do if we have a plus b in there. If we've got a product, we know what to do. If we've got it raised to a power, we know what to do. And if we've got it quotient, we know what to do. But that's it.
So what do you do then?
You can't do anything.
Well,
So this first term, all you can do is x squared plus 1. Nothing more you can do with that.
Okay?
So that's the gotcha on this problem. Now, what about this?
That's just to the 1/2.
1/2.
Gotcha. Okay.
Perfect. Good? All right. Now, let's see what you've learned and combine it all in this one monstrosity.
Indeed.
All right. Tell me what to write.
The natural log of x to just the first term, the numerator. Minus the natural log of the denominator. go faster than that, just 5x. 5 natural log of x.
Yeah, we can just skip that stuff.
Plus 2 the natural log of sine of pi to the x minus
1/3.
yeah 1/3 natural log x squared plus 2.
Nice. All right, so I think you get the rules now. After those couple of examples, you got it.
Okay.
That's exactly right.
Can you not split up that sine of pi to the x?
No. In here, we only have one thing, sine of a value.
Oh, yep.
Okay. So, I think we've kind of got it with our logarithm rules. Now, finally, let's learn how to take the derivative of a log. So, I'm going to calculate the derivative with respect to x of log base a of x. You with me?
Yeah.
Now, when I calculate that, that's going to be the limit as, I don't know which one we want to use. Should we use the h way?
Yeah.
As h approaches 0 of log base a of x plus h minus log base a of x all over h. You with me? This is what we're trying to calculate. This is the derivative of log,
Okay.
right?
Mm-hmm.
Going back to just our definition.
Yeah.
Now, I don't want to write this limit thing over and over again, so I'm just going to rewrite the inside, plate the inside, then we'll take the limit when I'm done. You with me?
Mm-hmm.
So we can rewrite this as, I'm going to pull the h out, so, well, I'll just write lim. I won't bother with the arrow down there. This is the limit as, we can pull the h out like this, and we can write 1 over h times the numerator, right?
Mm-hmm.
And then what is the numerator? Can I combine those together into one log?
If you divide it,
Right, so this is log base a of
x
x plus h over x. Remember, your log rules, they can go both ways. You can take a difference and put it back together in a quotient. You can take a quotient and separate it into a difference.
Oh, I see.
Make sense?
Mm-hmm.
And this is equal to the limit of 1 over h times log base a of, I'm just going to separate this as two fractions, so it's going to be 1 plus h over x.
Okay.
You with me?
Yeah.
And then finally, I'm going to bring this 1 over h up as an exponent, so this is equal to the limit of log base a of 1 plus h over x to the 1 over h.
Okay.
You follow that piece?
Mm-hmm.
And we were doing as h approaches 0. Now I'm going to do a substitution here. I'm going to let t equal h over x.
Okay.
I'm going to let t equal h over x, and notice that the limit as h approaches 0 is the same thing, logically equivalent as the limit as t approaches 0. If h goes to 0, t goes to 0.
Yeah.
And if
Okay.
t goes to 0, h has to go to 0. Because x is just a constant point. Make sense?
Mm-hmm.
Okay, so I'm going to rewrite this in terms of with t's in there. Now when I rewrite this 1 to the h, that one's going to look weird. Because I'm going to write it as 1 to the t times 1 to the x. Which is the same thing as 1 to the h. So make sure this makes sense. What is t? It's h over x. So 1 over t is the same thing as x over h. X's go out and we're left with 1 over h.
Yeah.
Okay.
So 1 over t times 1 over x is the exact same thing as that, is the exact same thing as just 1 over h. So putting that all together, this is now equal to the limit. I replaced all my h's, I got rid of all my h's, and now I just have t, so I'm going to write the limit as t approaches 0 now, of log base a of 1 plus t to the 1 over t times 1 over x. You follow that?
Yeah.
Using my exponent rule once again, I can bring this 1 over x out in front.
Okay.
You follow that?
Mm-hmm.
So this is equal to, and notice that x is also constant, so not only can I bring 1 over x out in front, I can actually bring it outside my limit. Because 1 over x has no t in it. It doesn't change as t approaches anything.
Yeah.
So I'm going to write my 1 over x here. 1 over x times the limit as t approaches 0 of log base a of 1 plus t to the 1 over t. With me?
Mm-hmm.
And now finally, the limit of a function of your input is the same thing as a function of the limit of your input. In other words, I can put this limit inside my function.
Okay.
So finally, this is equal to 1 over x times log base a of the limit as t approaches 0 of 1 plus t to the 1 over t. And what is this?
Just e.
It's just e. So this is equal to 1 over x times log base a of e.
Okay.
Make sense?
So whenever you take the derivative of the log, it will always spit out
Yep.
e. Okay.
Crazy, huh?
For every log?
Every log, doesn't matter what your base is. For any a, this comes out. E shows up all over the place. Now I'm going to rewrite this one more way using our change of base formula. I'm going to change my base from a to e.
Okay.
You with me?
So log of e to e.
So this is equal to, my 1 over x is still 1 over x, times, what's log base e of e? Okay, maybe just one step at
Oh,
a
it's
time.
just one.
So we have natural log of e
Mm-hmm.
over natural log of a. And natural log of e is just 1. So another way that we can write this is it's 1 over x times natural log of a, where a was whatever base you were taking the derivative of. Notice, if we were taking the derivative of natural log of x, so what if my a were an e here?
Then it would just be 1 over x.
Then it'd just be 1 over x. So that's why taking derivatives of natural logs are our favorite.
I see. Yep.
Because it just comes out 1 over x. So here's what it is in general, which, oh, I left it like this. I didn't apply the change of base when I said what we were doing. But it's often the case that we do apply the change of base to that and rewrite like that. Because we like things to be natural logs.
Yeah.
So here's more likely what you'll see as the common solution. And in the special case where we're just taking the derivative now of natural log, we know it's just 1 over x times dx, whatever, just apply the chain rule. So just to be very clear, we know now that the derivative with respect to x of natural log of x is equal to 1 over x.
Okay.
Special case, right?
Mm-hmm.
Okay, so now let's do some examples. Let's find the derivative with respect to x of natural log of 2x. What is that equal to?
1 over 2x.
1 over 2x times the derivative of the inside. You still have to apply your chain rule.
Oh, times 2. So
Times 2.
it's just x.
So it's still just 1 over x.
Oh, 1 over x, yep.
Okay.
Wait, so it doesn't matter if there's a constant or not?
It doesn't matter if there's a constant.
Inside
If you're
the...
curious, test it. What's the natural log of a times x? Well, that's 1 over a of x times the derivative of the inside, a.
Yeah.
No, it just comes out 1 over x.
What if x is the next one? Oh. What if x has the next one?
X is a function. or x is a linear function. You can't say, what if x wasn't x, and what if it was something like x squared plus 4?
I mean, what if you find the natural log of x squared?
Oh, well, let's do this one next. That's what you mean. Okay, so now let's look at the derivative with respect to x of x squared plus 3. What does that equal to? That equals, in our denominator, we're going to have x squared plus 3. And in our numerator, we're going to have...
This is the natural log, right?
Oh, sorry. I thought my dx was a natural log. Thank you. The derivative with respect to x of the natural log of that thing. Yes.
Okay.
Okay. So we have that in the bottom. What do we have in the numerator?
Just 2. 2x.
2x.
There you go.
Just the derivative of the inside. You better be able to calculate the derivative of the inside. Otherwise, we'll have to restart the class and we'll never get to calculus.
You mean physics?
Physics. Yep. My words are all sorts of mixed up today. Okay, so there's doing a couple derivatives with natural logs. Now, what about integrals? Let me just remind you of what we just showed. We just really showed that the derivative with respect to x of natural log of x is equal to 1 over x. We know that, right?
Mm-hmm.
Yeah.
Or in other words, the indefinite integral of 1 over x is equal to natural log of x plus c.
Okay.
Isn't the integral 1 over x way different than that?
We haven't been able to do the integral of 1 over x yet.
Yeah.
Here's how you wanted to do it before. Let me show you. The integral of 1 over x is the same thing as integral of x to negative 1,
Yeah.
right? dx. So what do? You add 1 to the exponent and you divide. So this is equal to x to the 0 over 0.
Oh.
This was the one that broke our chain rule, or broke our power rule.
Couldn't we do 1 over x squared though?
Yeah, we could do x to any power except negative 1, basically.
So it's just negative 1.
It's just negative 1 that we didn't know how to handle. With natural log, now we do know how to handle that.
Alright.
Interesting.
Make sense?
Yeah.
So now let's prove where the author starts with the definition of natural log. The author says, well, we'll just calculate it and point out how it's the definition. So now let's look at the integral from 1 to x of natural log of t dt. You with me?
Mm-hmm.
Okay, what's the integral of t? Or what's the integral of natural log of t with respect to t?
What is that?
What's the integral of natural log of x?
1 over x.
What's the integral of natural log of t?
Oh, 1 over t.
Ah, that's some quick thinking. There we go. Don't get confused because we change a variable. Now we evaluate it from 1 to x. You with me?
Mm-hmm.
Oops, I wrote 1 over t. No wonder you guys are confused. I keep writing this wrong. Don't let me. The integral of 1 over t is equal to... Okay, now I know why you're confused. I need to align my brain with what I'm writing. Okay. Integral of 1 over t is
Natural log of c.
natural log of t.
Plus c.
Well, when we're doing a definite integral, we just plug in the bounds, remember?
Yeah.
Okay. So now we plug in our bounds. So this is equal to, what do we get when we plug x into that?
Natural log of 1 over x.
Natural log of x, you just plug it in,
Yeah.
minus, what do we get when we plug in 1?
Natural log of
0.
Which is 0. So the integral from 1 to x of 1 over t, dt, forgot my dt, is equal to natural log of x. Now that's how the author defines it. He defines natural log of x is equal to the integral from 1 to x of 1 over t dt. And that's where he starts.
So he
Which now you can probably see why I hate that.
I can see why you hate it, but I mean, it makes sense.
It makes sense, but there's no reason for you to know that this has anything to do with logarithms. And then with this definition, he tries to go through and reprove our log rules, which are way easier to prove, just using logarithms.
I see.
So it makes a huge mess. I don't like it. Anyways, so that's what he gives us as a definition for a natural log of x. I think our way of coming at it is much, much better. And we've already not really needed the proof of this. Proof that the integral of 1 over x with respect to x is equal to natural log of x plus c. We already know that. Now, there's an absolute value in there, and we should probably talk a little bit about this absolute value. So imagine for a second I ask you, what's the natural log of negative 2 equal to? What is that asking? It's asking, so this is the same thing as log base e of negative 2 equals what? E to what exponent gives me negative 2?
I don't know.
Let's think about what e to the x looks like really quick and see where it gives us out a negative 2. So here I'm going to plot the function y equals e to the x. You with me? What's e to the 1? Or what's e to the 0, I mean?
That's
1. So let me just draw some rough lines on here. We only kind of need it accurate at the beginning. Actually, that doesn't really matter. Okay, so e to the 0 is 1. That's right there. What's e to the 1? E, which is like 2 point something. Up there, right?
Mm-hmm.
E squared, well, that's squaring that thing. It's not quite 9. Maybe it's close to 8. So we'll say it's close to 8. We're just trying to rough picture, right?
Yeah.
And then whatever. So this thing shoots up, and it shoots up fast. And it grows really, really fast. You with me?
Isn't e to the e 1? I mean, yeah, 1.
E to the e? Is 3 to the 3 1?
Oh, no.
Then why would e to the e be 1? Okay.
Okay.
Yeah, makes sense. Okay, now let's look at the other side. What's e to the negative 1?
1 over e.
That's 1 over e, which is a little bit more than 1/3.
Yeah.
Yeah.
So it's a little bit more than 1/3. And even if we go clear out here to e to the negative 10, e to the negative 10 is equal to 1 over e to the 10. E to the 10, that's a massive number. 1 over e to the 10 is a really, really small number. And so this gets closer and closer to 0 over here. Make sense?
Mm-hmm.
How big of a negative exponent do I have to plug in there to make e negative?
You can't.
You can't. I can't make e negative. There is no exponent such that e to that exponent gives me negative 2.
Interesting.
Make sense? So we cannot take logs of negative numbers. Doesn't make sense. So that's why we have this absolute value.
Okay.
It only makes sense with positive numbers. Good?
Mm-hmm.
Okay. So now we'll apply what we know to solve an integral. So we're looking for the integral from minus pi halves to pi halves of 4 times cosine of theta all over 3 plus 2 sine of theta d theta. You with me?
Yeah.
Now, let's go back and write what we know in a slightly different way just to help you see things. I know that the integral of 1 over u times du is equal to natural log of u plus c, right?
Mm-hmm.
Or in other words, if I put the du on top here, du over u, when I take that integral, I get natural log of u plus c. So if I can express something as u du over u, then I can do this integral. So I want a u substitution that gives me something like du over u when I'm solving these. Does that make sense?
Okay.
So what's my u going to be? Take a shot in the dark.
2 times sine of theta.
2 times sine of theta, that would be an okay guess. A better guess is u equal to 3 plus 2 times sine of theta. Always include the constants if you can, because remember, it doesn't make taking the derivative any harder.
That's
And it
right.
just helps clean it up, so we don't have this dangling 3 down there.
Okay.
But you could have just used 2 times sine of theta and it still would have worked. The algebra is just a little bit messier. Okay, what's our du?
It's
Two
just-
cosine theta,
It's what?
right?
It's d theta.
We'll put that last.
It's just two cosine theta.
It's 2 cosine theta. Come on, guys. Let's line you up on this. What's the derivative of sine?
Cosine.
Cosine.
But what about your 2?
The constant
Yeah.
just stays. How do you guys get stuck on the same thing? If I look at the derivative with respect to x of 5 times x to the 4, what does that equal to?
20x.
You kept the 5. Why don't you call 4x to the 3?
But if it's just 5x, then it's just 5.
Right. You still had 5 instead of 1. You kept the 5 there.
Oh. Okay. I see.
Okay, the product is always showing up all the way through. It's when you're adding constants that it doesn't show up in your derivative.
I see.
Products always show through. The way that you can see that from the definition of a limit, or from the definition of a derivative, the limit as n, or as h approaches 0 of a constant, some constant c times the function of x, we can always pull the c outside the limit. It's always going to be c times f prime of x.
Yeah.
Yeah.
So since we can pull constants outside of limits, we can always think about ignore the constant, take the derivative, okay, times the constant back in. Okay, anyways, so here's our substitution. Anyways, if du is equal to this, well, let's just write it now. So this is the integral from, remember we got to change our bounds. We'll come back and change our bounds in a second.
Okay.
In our denominator now we have a u. What do we have in our numerator? Du takes care of 2 cosine d theta. We have 4 cosine d theta, so we still have a 2 there.
Okay.
Make sense?
And then you can take the 2 out, right?
Then you can take the 2 out. But let's change our bounds really quick.
Okay.
So when we plug in minus pi halves in for theta, what is u?
Sine of minus pi halves is just -1. So it's just 1.
You follow that? Plug in minus pi halves for sine. That's -1. We're talking about the bottom of the circle. Y coordinate of the bottom circle is -1. Negative 1 times 2, -2. 3 minus 2 is just 1.
Okay.
Okay, what about the top?
5.
5. Yeah. Top of the circle, sine's 1. 1 times 2 is 2, plus 3 is 5. Okay, and then this is also 1 to 5. Okay, so this is equal to 2 times the natural log of u evaluated from 1 to 5, which is equal to what?
Just 2 times the natural log of 5.
Which is 2 times the natural log of 5. We minus 2 times the natural log of 1, but natural log of 1 is just 0. So that's why he's skipping that. Let me pull up the book, because I think these come from the book now, just to make sure I'm not making any obvious mistakes. Did I send you guys the updated syllabus?
Yeah.
Okay. Let's see, we're in section 7.2.
Mhm.
7.2, and not in those examples yet. We're on this example, 2 natural log of 5. Okay, so we didn't make a mistake. All right.
Okay.
Next, coming over here. Hopefully this is charged enough now that I don't need that. Yeah. Okay. So now looking over here, I'm going to do a bunch of these. So notice that up till now, we only knew how to take the integral of sine and cosine out of our trig functions. We didn't know how to take the integral of tangent, cotangent, secant, and cosecant. Well, with logarithms, now we can. So let's prove what each of these are. So the integral of tangent of x dx is equal to, remember, what is tangent?
Sine over cosine.
Sine over cosine. Sine of x over cosine of x dx, right?
Yeah.
Now, if I'm going to use logarithms, I want my u to be cosine of x.
If it's cosine, is it a negative sign?
And so du is equal to negative sine of x dx, right?
Mm-hmm.
So this is equal to the integral of negative du over u, right?
Okay.
Which is equal to negative natural log of u plus c, absolute value of u, in case our thing can go, we don't like a negative.
Okay.
So we have negative natural log of u plus c, but remember, since we don't have our bounds, we got to plug back in. One of you on your test did an integral like this and didn't plug back in. You left it in u's. So this is equal to negative natural log of, what's u?
Cosine of x.
Cosine of x. Okay, that's not what we got. We have a secant here.
Yeah.
How are we going to get that? What can we do with this negative? We can bring it up as an exponent.
Oh.
Which is 1 over cosine, which is secant.
Which is natural log of secant, sorry, that should be an absolute value, of x plus c. You see it?
Yeah.
Yeah.
Alright, let's do cotangent now. The integral of cotangent of x dx is equal to the integral. This time we have what? We have cosine of x over sine of x dx. Now, if we let u be sine of x, then du is cosine of x dx.
Yeah.
So this is still u over du. So it's just going to be natural log of sine of x plus c. You see that?
The natural log of sine of x plus c.
Mhm.
Okay.
Because this is our whole u. That whole thing is du. And so we're just left with natural log of u. You with me?
Mm-hmm.
Okay. But that's not what we have over here. We have a negative cosecant. Well, sine is the same thing as 1 over cosecant. So I can call this cosecant of x to the minus 1 plus c, pull the minus 1 out, and it's equal to negative natural log of cosecant of x plus c.
Why would you want to do that?
Just because when we take derivatives of tangent, secants come out. When we take derivatives of cotangents, cosecants come out. And so it's keeping tangents associated with secants and cotangents associated with cosecants. Just supposed to make it easier for you to memorize, so you don't have to read the derivatives. Obviously, just leaving that sign would work just fine. But think for a second, what's the derivative of tangent? It's secant squared.
Yeah.
What's the derivative of cotangent?
Negative cosecant squared.
And you still have your negative, you still have your positive, you still have a secant, you still have a cosecant. So
Okay.
writing it this way is just supposed to help you memorize it better. Make sense?
Mm-hmm.
Yeah.
Okay. And now let's look at the integral of secant. Now this one is a weird proof, because we're going to do something strange. We're going to multiply top and bottom secant of x by secant plus tangent of x. I know, it feels weird. So this is equal to the integral of secant of x times secant, I was going to do that, secant of x plus tangent of x, all over secant of x plus tangent of x. You see what I did there?
Yeah.
Now, if we let u equal secant of x plus tangent of x, what does du equal?
d
What's the derivative of secant?
Is
Secant times tangent.
Yeah. Yeah.
Oh, no, yeah.
What's the derivative of tangent?
Secant squared x.
You with me?
Okay.
This is all times dx, right?
Mm-hmm.
Now I'm going to factor a secant out of both of those and reverse the order that I write them in. So du is equal to, if we factor a secant of x out of both of those, we get secant of x times, and I'm going to write this term first, secant of x plus tangent of x dx.
Cancels out nicely.
And that is exactly what this is,
Mhm.
numerator there. So that says now du over u. So when we calculate its integral, it's going to be the natural log of secant of x plus tangent of x plus c. Follow that? And then cosecant is similar. The trick is multiplying top and bottom by cosecant of x plus cotangent of x. I don't know if we need to see any more of these. I think you get it, right?
Yeah.
Okay, so now let's move on to calculating one of these integrals the way that you might see on your homework. So we have the integral from 0 to pi 6 of tangent of 2x.
Mm-hmm.
Now, if the 2x is throwing you off, obviously we can do a u substitution. We could say u is equal to 2x, du is equal to 2 dx, and do a substitution like that. And so we can rewrite this as equal to the integral of 1/2, bring the 1/2 out in front, tangent of u du.
Okay.
Right?
Yeah.
Now if we do that, we just need to quickly change our bounds. If we plug in 0 for x, u is still 0. If we plug in pi 6 for x, u is pi thirds. You with me on that?
Yeah.
Okay, now this whole thing is equal to 1/2 times, what's the integral of tangent of u?
Natural log of secant.
Natural log of secant of u, evaluated from 0 to pi thirds.
Okay.
With me? So this is equal to 1/2 times, what's the secant at pi thirds? Secant is 1 over cosine, right? So what's cosine at pi thirds?
It's root of 3 over 2.
Other one?
1/2.
1/2. The x coordinate when we're pi
Oh,
thirds
yeah, pi 6.
is 1/2.
Gotcha.
Yes. So secant at pi thirds then is
1/2.
no 2, the reciprocal. Cosine was 1/2, so secant is 2, the
Gotcha.
reciprocal of 1/2.
Mm-hmm.
So we have natural log of 2 minus the natural log of, where is secant equal to 0?
Well, cosine of 0 is 1. So it's just 1. Secant of 1.
Is that possible?
So it's just
It's not
natural
possible.
log of 1.
Did we mess something up? You're getting 1? Oh, duh, 1.
Yes.
I asked the question weird. Secant of 0 is the same thing as 1 over cosine of 0 is 1. Yeah, I think me and Jeremy were both thinking the same way, which doesn't work. I was right for a second. Okay. Anyways, a natural log of 1 is
Natural log of 0.
0. So this whole thing is 1/2 natural log of 2.
You always want to leave your answer in natural logs.
Yeah, don't get rid of natural logs. There's no way to get rid of the natural log.
Okay.
Let me find 1/2 natural log of 2. Okay. Next, last thing natural logs are very useful for is helping us calculate the derivatives of complex fractions, of rational fractions. And it has a special name. It's called logarithmic differentiation. So if I were to ask you to calculate the logarithm of this thing, or the derivative of this thing, that could be kind of a nightmare. Let's just make it hard on ourselves. Let's pretend that there's a 5 right there. Okay. You don't want to calculate the derivative of that, do you? That sounds like a nightmare. So here's the big trick on how to do derivatives of terms like this. The trick is to take the natural log of both sides. So if I know that y is equal to this whole thing, then I know that natural log of y is equal to natural log of that whole fraction. X squared plus 1 to the 5 times x plus 3 to the 1/2 all over x minus 1, right?
Yeah.
Same thing I told you when we were talking about over here. I said sometimes we're going to take the natural log to use that to split it up into a bunch of pieces, and then we'll figure it out from there.
Okay.
So natural log of y is equal to this thing. And let's rewrite that out.
5.
Yeah, let's do this one step at a time. This whole thing is equal to, we have natural log of, you want to do it all in one go?
Yeah.
Okay, so let me know what's right.
5 times the natural log of x squared plus 1 plus 1/2 the natural log of x plus 3 all minus just the natural log of x minus 1.
Perfect. You with me? So now I'm going to take the derivative of both sides. And by both sides I mean this and then this. You with me?
Yeah.
So what's the derivative of natural log of y?
What is that?
It's 1 over y.
What's the derivative of natural log of y?
1 over y.
1 over y
dy dx.
dy dx times y prime. Perfect. Chain rule. You also have to take the derivative of y with respect to x. We're doing the derivative with respect to x. I probably didn't say that, but that's my math. You with me?
Okay.
Okay. What's the derivative of this term?
It's
Write the denominator first, that's easiest. X squared plus 1, right?
yeah.
And our numerator is going to be 5 times the derivative of the inside. What's the derivative of the inside?
2x.
2x times 10x. Plus, this time we have the 2 is still in the denominator. 2 times x plus 3. 1, right?
Mhm.
Minus 1 over x minus 1.
Okay.
So then what does y prime equal? Y prime equals all of this times y.
Yeah.
You see that?
Okay.
Might need a little bit more space. So all of this, so we have 10x over x squared plus 1 plus 1 over, I'll say 2x plus 6, minus 1 over x minus 1, all times y. What is y?
Y is.
It's
What
that
is
thing.
that? Yeah.
X squared plus 1 to the 5 times x plus 3 to the 1/2 over x minus 1. Now don't mess with this anymore. There's your answer.
That seems pretty messy.
Seems pretty messy, but really you have 3 different terms with a bunch of stuff factored out, pretty much everything you could factor out. So it's actually pretty nicely factored. It's just the fact of the matter, if you do take the derivative of that thing, you're going to get a messy answer.
That's right.
Now, could you imagine trying to apply the quotient rule and the product rule to that thing, figure that out, keeping track of everything, all your chain rules would blow up.
Oh yeah.
Whereas this was not bad at all.
Okay.
So one more way that natural logs are super useful. Okay, so that's it for natural logarithms. Now we talked about their inverse function, the exponential. If I know that y is equal to natural log of x, I know that x is equal to e to the y. This is the inverse function of this. Make sense?
Yeah.
Okay, since it's the inverse function of it, let's really quick draw out both of these to give you a rough idea of what they look like. We already talked about e to the x, what that looks like. If I graph e to the x, then that's a function, it goes through the point 0, 1, and it looks like this. That's what an exponential looks like. Then what does a logarithm look like? What does the inverse of this thing look like?
Shift it.
Well, this one went through 0, 1, so this one goes through 1, 0.
Mm-hmm.
This one gets closer and closer to the x-axis, so this one's going to get closer and closer to the y-axis. So this one's going to shoot up like this. Something like that. So this is roughly what natural log of x looks like. This is roughly what e to the x looks like.
Okay.
Okay.
Make sense?
Yeah.
They're inverses of each other. Which means if you take a natural log of something smaller than 1, you get negative numbers.
Well, I thought we couldn't do that though.
You can't take the natural log of a negative number. But if I take natural log of 1/2, I'm going to get a negative number.
Really?
Yes, and it makes perfect sense. E to some negative exponent is going to give me 1/2. E to the 0 gives me 1.
Yeah.
Let's not use e. This is throwing you off. Let's really quick do log base 2 of 1/4. What does that equal to? Negative 2. We should have done some of these to help you see it. What's 2 to the negative 2?
1/4.
1/4.
Okay.
How is it 1/4?
2 to the negative 2 is equal to 1 over 2 to the 2. You with me?
Yeah.
And if we wanted a bigger negative number, like negative, well, if we plug in, if we want a bigger, well, I'm not sure which way to say this. If I did something like 1 over 1024, plug in a really small number there, and this is going to be negative 10.
Yeah.
Make sense? The smaller the number we plug in here, the bigger our negative is.
Alright.
And so this thing shoots down to negative infinity. E is no different than 2, they're just different numbers.
Okay.
Make sense? It's good to have some basic intuition for what these functions look like. On how to think about them. Graph and note that they're inverses. Okay, we did that. This is just for your calculator. Oftentimes on a calculator you see an EXP button. So you do EXP and then you give it an X, some number. EXP and then you give it 2. That spits out e to the 2. That's what the EXP on your calculator means. In case you didn't know that, I will never reference this EXP again.
Alright.
Okay. Some other useful things to know. What's e to the power of the natural log of x?
It's just e to the 1 over x.
What is e to the natural log of x? Okay, let's start the other way. Let's look at this one. What's natural log of e to the x equal to?
X.
1 over x.
Just x.
What?
Okay. Log base e of e to the x is equal to,
What would you guys say?
X.
back over here, log base pi of pi to the 5 was equal to,
Oh, just x.
what exponent do you have to raise e to get e to the x?
X.
X.
Okay.
Wonderful. So log base e of e to the x is equal to e to the x. Now, e to the natural log of x, let's look at that. E to the natural log of x, what's that going to be equal to?
The natural log of x.
Taking the natural log of something gives you a number, and you're saying raising it to the power of e doesn't change it?
Yeah.
Okay, that's wrong. Typically,
Yeah.
e to its power, because if I take the natural log of x and it came out 5, and then I take e to the power of 5, that's not still 5. It's a much bigger number.
Oh, yeah.
natural log and e are inverses of each other.
Yeah.
Okay.
So they undo each other.
So it's just one.
So it's just x. Look, back to basic. If I know that y is equal to f of x,
Yeah.
how did I say this last time? I'm trying to remember. If y is equal to e to the x, then that's the same thing as x is equal to natural log of y, right?
Yeah.
So when I plug these functions into each other, they undo each other. You remember going back to what is, or if we want to write this in terms of y, the inverse function would be y is equal to natural log of x, if you want to think about both as functions of x. So if you write it like that, then remember that when we do f of f inverse of x, that's the same thing as f inverse of f of x is just equal to x.
Yeah.
And that's what we're doing here.
Uh-huh.
One function, then the other.
Okay.
Make sense?
Yep.
Okay.
So e's undo natural logs, and natural logs undo e's. You with me?
I think so.
Now, in case you just can't see it and need to play with it for a second, so if we have e to the natural log of x, what is that equal to? We'll just say y for a second. We're trying to figure out what that y is, right?
Okay.
Take the natural log of both sides. Now I know that natural log of e to the natural log of x is equal to natural log of y, right?
Mm-hmm.
Natural log cancels out, or pull the exponent out. So now I get natural log of x, pulling the exponent out, natural log of x, times what's natural log of e? 1 times 1 is equal to natural log of y, or in other words, x is equal to y.
Okay.
And so this is just x. They undo each other.
Okay.
But I don't really want you to memorize how to figure out how to calculate these things. I want you to kind of memorize that natural logs and e's undo each other. They're inverse functions. E to the x and natural log of x are inverse functions. They undo each other. Make sense?
Yeah.
Okay. Because that's crucial to know for a bunch of problems that we have to solve. So this is x, this is x. Okay, so let's use this to solve a quick algebraic expression. You've gotten this in your college algebra courses, something like it. E to the 2x minus 6 is equal to 4. And our job is to find x.
Okay.
How do I do that? I take natural log of both sides. Natural log of e to the 2x minus 6 is equal to natural log of 4. Natural log of e just gives me the exponent. Remember, log gives me the exponent.
Mm-hmm.
So we just have 2x minus 6 is equal to natural log of 4.
Okay.
Or 2x is equal to natural log of 4 minus 6.
Plus 6.
Or plus 6, thank you. Divide both sides by 2. I get x is equal to 1/2 natural log of 4 plus 3.
Mm-hmm.
Now, 1/2, I can put that as an exponent inside of there.
Oh.
So x is equal to natural log of 2 plus 3.
Yeah.
If I bring the 1/2 as an exponent, that's 4 to the 1/2, which is 2.
Okay.
Okay. So now, find the line that passes through the origin and is tangent to the line y equals natural log of x at some point. Okay, that's kind of a complex problem to do, guys. Okay, our natural log function, what does that look like? It looks roughly like this. You with me?
Mm-hmm.
Now, at any point on this function, I can find the tangent line to that point. Right? You remember tangent lines?
Yeah.
Now, if I come and I find the tangent line at this point, notice that that's going to be a line something like that, right?
Okay.
It's basically saying, find the point where its tangent line goes exactly through the origin.
Okay.
So there's going to be one and only one tangent line that goes through the origin. And so our job is to find the point essentially, I need to find the A such that at A, the tangent line goes exactly through the origin.
Okay.
That's another way to think about it. So find the line that passes through the origin and is tangent to y equals natural log of x at some point.
Okay.
So we're trying to find the equation of this line. You with me?
Yeah.
Now I know that this line goes through the origin, so I know that it's of the form y equals mx. I don't need any plus b on there,
Okay.
because it goes through the origin. You with me?
Mm-hmm.
So really I just need to figure out what the slope is,
Which is the derivative, right?
which is the derivative.
Okay.
So I know that my m is equal to, now whatever this a is, we don't know what this a is, we're going to figure out what this a is. I don't know what it is yet.
Okay.
But I know that m is equal to f prime at a, where f of x is equal to natural log of x. You with me?
Yeah.
Mm-hmm.
At some point a. This is the a we're looking for. But whatever it is, I know that f prime of a is equal to what?
D over dA of the natural log of x.
What's f prime of x?
D over dx of the natural log of x.
Is this 1 over x?
It's just 1 over x. What's the derivative of natural log of x with respect to x?
That's right.
Just 1 over x. So what's f prime at a?
1 over a.
1 over a. So I know that the slope of this thing is equal to 1 over a.
Okay.
So let's see what else I know. I'm not just figuring this out fly, so. Let's see, I also know that the slope, so I know 1 over a is equal to, I also know the slope is equal to rise over run, right?
Yeah.
So the slope of this line is going to be this height over this distance. What is this height?
1.
It's the height of the function. What's my height of my function at the point A? It's just f of a.
Mm-hmm.
Oh, so it's the natural log of a.
So natural log of a. And what's my run?
It's
Just a.
Just a. You with me?
Okay.
So is this getting us anywhere? So I know that this gives me that multiply both sides by a. So I know that 1 is equal to natural log of a.
Times a.
No.
No.
Where'd your other a go then? Oh, you're right.
So my a is 0. That's wrong. Why didn't that work? Why am I getting 0? A is a point such that 1 over a is equal to natural log of a over a. Maybe we're losing an answer by dividing by a's. So let me rewrite it this way. A is equal to a times natural log of a, right?
Mm-hmm.
Let's bring all my a's on one side. So a minus a times natural log of a is equal to 0. So a times 1 minus natural log of a is equal to 0. Natural log of a is 1, which is 0. I'm missing something. Let's see, where are we? Oh my goodness, I can't believe I was being this sick. Okay, we were thinking about this right the whole time. When is natural log of a equal to 1? What's the magic a that makes that true?
The magic a that makes that true?
Yes. Log base e of what is equal to 1? What should I put there? Not 0.
E.
E. Right?
Okay.
Oh, so E is the.
So a is equal to e. E is the point. So our a is e. Wow, can't believe we got stuck like that. Kept saying you need to take natural log of 0 to get 1. No, you can't take natural log of 0. Right? Can't plug 0 into our natural log function.
Yeah.
Wow. Good thing we didn't catch on camera, huh?
Yeah.
For the world to see. Okay. So that takes care of that column. Let's see, can I see my next column still? Oh, I can see the whole whiteboard. So just keep using the space over here. Now proof that the derivative with respect to x of e to the x is just e to the x. Okay, that's our next proof. So if I know that y is equal to e to the x,
Okay.
and I want to find y prime, you with me?
Mm-hmm.
Well, then natural log of y is equal to natural log of e to the x is equal to what?
Just x times the natural log of e.
These are inverse functions.
Oh, just x.
Just x. There we go. So natural log of y is equal to x. You with me?
Mm-hmm.
Take the derivative now of both sides. What's the derivative of natural log of y?
1 over 1
Times
y prime
y prime is equal to
x.
1.
1.
Taking the derivative of both sides.
Okay.
You with me?
Yeah.
So then, y prime is equal to what?
1y.
Is equal to y, which is equal to e to the x.
Okay.
So the derivative of e to the x is
E to
E
the
to
x.
the x.
e to the x. How hard is that?
How does that work though? That doesn't make sense to me.
That means that e to the x is the special function. My picture's going to lie because I can't draw a good picture. But e to the x is a special function such that the height of the function and the slope of the function are the same at every point. If this has a height of 10, the slope here is 10. So if you were to draw a tangent line through here
Yeah.
at height 10, the slope of this tangent line would be 10. Here at 1, if you were to draw a line through there, the slope would be 1.
On the whole thing?
Right here, draw a tangent line through there. What's the slope of the tangent line? 1. A tangent line only has one slope for the whole thing.
That makes sense.
So whatever the height of the function is also its slope. Notice that the height of the function here is really, really small, and its slope is really, really small.
Mm-hmm.
The height of the function here is really, really big, and its slope is really, really big. The height of the function is never negative, and its slope is never negative.
Okay.
Is there something like that for natural log?
This is it. This is a function. E to the x is another way that I've heard people define e. What is e? It's a special number you can plug in for a such that a to the x is equal to a to the x prime. It's a special function whose height is always equal to its slope. That's what function it is.
Okay.
So its height is always equal to its slope. Now notice, e to the x, this is crazy. Not only is its height always equal to its slope, its height is also always equal to its concavity.
Concavity.
Yes, take the derivative again to calculate its concavity.
Oh, yeah.
And if we had a word for taking that other derivative, it's also equal to that. And it's also equal to that.
Circle.
Y is equal to y prime, 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 plus m prime 0 as you want. Take the derivative as many times as you want, it doesn't change the function.
So how do you...
In other words, if your position function, for example,
Okay.
if your position function at a time were equal to e to the t, then your velocity would also be e to the t, and your acceleration would be e to the t, and your jerk would be e to the t.
That's weird.
It's this crazy function. No matter how many derivatives we take of it, we still get the same thing.
how does it happen in the real world then? Like, how is something at position e to the t moving at e to the t at a speed
It's
of
following
e to the
this
t?
path. If it's following this path, that's what's happening.
Okay.
So e to the x is a very wonderful function. You love every time you see it. It makes life easy, and it shows up all over the place. Now, trick question. What's the integral of e to the x with respect to x?
Just e to the x.
E to the x. Plus a constant. Don't forget your constant.
Sweet.
Okay.
Good? Real
Right.
hard math.
If you do the integral of the integral of the integral, it's the same thing, right?
Same thing,
Okay.
but not quite, because you get the constant there.
Oh.
Because then when you integrate, that constant could then have an x multiplied to it.
I see.
So not quite.
Okay.
If the constant were always 0 each time you integrated, then yes. Good? Okay, so let's calculate some derivatives. What's the derivative with respect to x of 5 times e to the x?
Just 5 times e to the x.
5 times e to the x. Okay. What's the derivative with respect to x of e to the negative x?
E to the negative x.
E to the negative x times, don't ever forget your chain rule. Chain rule applies to everything. Anytime you're doing a derivative, always and forever, you have your chain rule.
Okay.
Times,
1.
not 1,
Negative 1.
negative 1. What's the derivative of that?
Oh, I see.
Negative 1. So it's equal to negative e to the negative x. Right?
Okay.
What's the derivative with respect to x of e to the sine of x?
E to the sine of x
E
times
to the sine of
cosine.
x times cosine of x.
Okay.
Alright, what's the derivative with respect to x of e to the square root of 3x plus 1?
E to the square root of 3x plus
E to
1
the square root of 3x plus 1 times the derivative of this thing. What's the derivative of that? Let's just write that down here and then we'll go back and plug it in. The derivative of this is going to be 1/2 times 3x plus 1 to the minus 1/2 now
Times 3.
times 3. You with me?
Yeah.
y to the minus 1/2. And
Because you
You have to
subtract
go
1.
down.
We brought the 1/2 down and minus 1. Gives us a negative 1/2.
Okay, where's your times 3?
It's on the side.
From this.
Okay.
We were calculating now the derivative of 3x plus 1 to the 1/2. What's the
Oh,
derivative
it's
of
a chain
this?
rule inside a chain rule inside a chain rule.
Yep,
right?
chain rule side chain rule. Yep, that's
Okay.
recursive. All the way until you get a 0 from your chain rule.
Okay.
Or I mean a 1.
Gotcha.
Right?
Okay, so this is a derivative of this right here, which is that piece. So we gotta go plug that in right here. So this is going to be times 3 over 2 square roots of 3x plus 1. Right?
Yeah.
Okay, there's our derivative. Not so bad. Okay. Prove that the integral of e to the x with respect to x is equal to e to the x plus c. We already did that. How do you prove it? You show that the derivative of e to the x is e to the x. And then an integral is any antiderivative plus a constant. So we're already done with that. So let's calculate those two integrals now. What is the integral from 0 to natural log of 2 of e to the 3x dx?
3.
If you're ever getting stuck, always just let u equal 3x, then du is equal to 3dx, right?
Yeah.
And so this is going to be equal to what?
E to the u.
Well, just integrate it now. So we'll need a 3, so we'll have 1/3 e to the u evaluated
From 0.
from 0 to natural log of 2, right?
Okay.
You should change it to,
Good?
Mm-hmm.
Okay? So when we plug in natural log of 2,
You just get
we can keep the 1/3 out if we want to think about it like this. Okay, so this is e to the 3 times natural log of 2.
it's just 3, right?
The natural log of 2 is the natural log of
No, it's not 3. We'll see how to mess with that here in a second. Minus e to the 0 is
1.
1. Follow that? Now, what is 3 times the natural log of 2? Ignore the e for a second.
It's natural log of 8.
It's natural log of 8, right? I can bring that 3 as an exponent to the 2.
The natural log of 8?
2 cubed.
I'm still lost.
So 3 times the natural log of 2
Mm-hmm.
is equal to natural log of 2 to the 3
Oh, yeah.
is equal to natural log of 8.
Okay.
Okay, so now what's e to the power of natural log of 8?
8.
8. E's and natural logs undo each other.
But why is the 8 still left?
Natural log of e to the 8 is, natural log of e to the 8 is equal to e to the natural log of 8 is equal to 8.
Okay.
They undo each other.
Yeah.
Okay, so this is equal to, we'll write down here, so this whole thing is equal to 1/3 times
8 minus 1.
8 minus 1, 7, which is equal to 7/3. Good?
Yeah.
Okay.
See if, see if I can find that exercise, make sure we didn't make any small mistakes. Oh, that's part B. 7/3, okay. Okay, next one is that next integral I had written and lost over there. Integral from 0 to pi halves. Of e to the sine of x. Am I mixed up what I'm looking at? No.
No.
E to the sine of x times cosine of x dx. Okay, obviously we need u substitution. What's our u going to be?
Sine of x.
Sine of x. So our du is equal to
Cosine of x.
cosine of x dx. So when I calculate this integral, it's going to be equal to you don't see it in the u's in there?
No, I don't.
Okay, let's put the u's in. So if we're going to put our u's in, let's change our bounds. If x is 0, what's u?
0.
0. Sine of 0, 0. If x is pi halves, what's u? 1. So we have e to the u du. Follow that?
How does the... Oh, yeah. I see.
That's a cosine.
Yep.
Okay. What's the integral of e to the u?
Just e
E to the u. And we're evaluating that from 0 to 1, which is equal to, what do we get when we plug in 1? What do we get when we plug in 0?
1.
E minus 1. That's our answer.
Okay.
Remember that e is a lot like the number pi. The same way that you'd leave pi minus 1, that's perfectly fine. E minus 1 is perfectly fine as well. Good?
Mm-hmm.
Now I go through a lot of pains of showing that exponentials and derivatives are the same way. Okay, so now here's how he defines a to the x. He defines a to the x. I don't need to do the proof here. The whole step is just one little step. He shows that a to the x, he defines a to the x. We'll prove it's equal. He just defines. He defines a to the x as e to the x times natural log of a.
Okay.
That's his definition. We're just going to prove it because we came up with a different definition for e. We use this definition for e. We use different definition from the beginning. We use exponents to define all this to begin with. Anyways, So let's prove it. A to the x is the same thing as a to the x. You see how this is just a,
Yes, now I
and
do.
the
Yep.
e and natural log undo each other, and you're left with a. And now, just multiply the x in there and change the order that you're writing.
But when you put a in the exponents and then the exponent, that doesn't it just multiply instead of work like an exponent? Like is
When I bring the x in here,
yeah.
when I bring the x in here, then it's x times natural log of a.
Yeah.
Isn't that different from a to the power of x?
Let's keep messing with it so you can see one more step. E to the x is equal to natural log of a, right? Let's write down our next step. Now since x is in front of natural log of a, I can rewrite this as natural log of a to the x. You with me?
Okay.
And e and natural log undo each other, and we're back to a to the x. So went full circle on it. Good? Okay. Now why do we do that? Because e is way easier to work with as a base to do math with than a random a. It's way easier to work with e to the 10 than it is e to the x than 10 to the x. So now we can convert any exponent we see. If we have a 10 to the x, we can rewrite that as an e to the x with some other number in there.
Okay.
You with me? And that helps us solve a bunch of problems that seem like they'd otherwise be an absolute pain. Let's get a slightly bigger piece of chalk, not much bigger. So now let's use that to try and solve a problem that at first might seem, where do you even begin? Let's look at the derivative of x to the power of x.
Okay.
So I'm looking for the derivative with respect to x of x to the power of x. How on earth would we do that? Because you have a variable to the power of a variable. You don't have 10 to the x, we can figure out how to do that. You don't have x to the power of 10, we know how to do that. It's x to the x.
Can't you just pull it down and then just say x minus 1?
That's what you do here.
Yeah.
That's not what you do here. Should we calculate this one first? Let's calculate something like that first, just to get a feel for this.
Okay.
All right, 10 to the x. 10 to the x can be rewritten as e to the x times natural log of 10. You with me? What's the derivative now of that? So if we do the derivative with respect to x of this thing, then we get, what's the derivative of this?
What
What's-
is
It's still just e to the x times natural log of 10, same thing you had before,
Yeah.
times the derivative of the inside. What's the derivative of x times the number?
Just
1?
Just the number. This is a constant. Natural log of 10 is just some number. It's just a constant. Like 3.
Yeah.
If this were x times 3, what would its derivative be?
Oh, I got you.
So it's just natural log of 10.
Mm-hmm.
Okay? Notice that we did not write x times 10 to the x minus 1.
Okay.
Okay.
You see how those are drastically different?
Yeah.
So now the derivative of x to the x, this one is especially weird, because we have an x in the base and an x as the exponent. So we're going to use the same trick, rewrite this in terms of e's. So this is the derivative with respect to x of, using this formula over here, it's going to be e to the x times natural log of x.
Okay.
You with me?
Mm-hmm.
Now we can take the derivative of that, and that's real easy. What is it? It's still e to the x times natural log of x times, now we got to take the derivative of this whole thing.
Natural log of x.
No, that's a product rule. You have two functions of x. You have x times natural log of x. You get the derivative derivative of the first multiplied by the second plus the derivative of the second multiplied by the first.
Okay.
Natural log of x is a function
Yeah.
of x. X by itself you can think about as a polynomial function. Product rule. Okay, so we gotta do the derivative of the first multiplied by the second. What does that give me?
Natural log of x.
Plus the derivative of the second.
Isn't that 1 over x?
Multiplied by the first.
What?
1.
Okay.
You did it. There we go. That's what it is.
Do we get to see an example?
That was an example. I don't know what you mean. We just barely found out the derivative of x to the x. That was a function.
But that answer just seems messy.
The answer seems messy. Okay.
Okay.
Nothing wrong with that. If I said, okay, what's the slope now of this function at 3, you can figure it out. You just plug 3 into this.
3 for x?
Yes.
Well,
Natural log of 3, that's just a number. Plus 1, still just a number. 3 times natural log of 3 is just a number. E is just a number. E to that power is just a number. You can't tell you spit out a number. Same as anything.
Okay.
And that would give you the slope at that point of this function.
Gotcha.
Still just all numbers. Okay. Proof that the derivative of a to, we basically just did this, but we'll do it again. So now what's the derivative with respect to x of any constant a to the x? Well, that's going to be the same thing as the derivative with respect to x of, rewrite a to the x this way. E to the x times natural log of a, not x, a, right?
Mm-hmm.
Okay, now take our derivative. This is equal to e to the x times natural log of a, all times natural log of a.
Yeah.
Is a constant?
Yes, it is just some number.
So why would you want to do that instead of x times a to the power of x minus 1?
Well, this is saying, imagine I ask you to find the derivative of 3 to the x. How would you find that?
Oh, you're right.
You'd use this formula. Okay, now this is equal to e to the x times natural log of a is still just a of x, and then times natural log of a. So you can rewrite it that way if you want.
Okay.
Which is how we have it written here. The derivative with respect to x of a to the x is a to the x times natural log of a. So now you can figure these things out really quick. What's the derivative of 3 to the x? It's 3 to the x times natural log of 3.
Mm-hmm.
Make sense?
Mm-hmm.
Cool. Integral now. The integral we get for free. It's just an antiderivative, right?
Yeah.
So looking at this, if I know that the derivative of a to the x is a to the x times natural log of a,
Yeah, I see.
then what's the derivative of a to the x over natural log of a?
The derivative of that?
What's the derivative of this?
A to the x.
A to the x. So the antiderivative of this is this,
Gotcha.
plus constant.
Mhm.
Remember, what's the solution to an integral? Any antiderivative you can think of, plus a constant. Here's an antiderivative.
Okay.
So once you find one antiderivative, you know how to integrate. Okay, more examples. If y equals 3 to the x, what's y prime?
Y prime?
So if y is equal to 3 to the x, y prime is equal to,
E times.
just take the derivative.
It's just 3 to the x.
Oh, 3x
natural
times.
log of
Okay.
3 to the x times natural log of x. Okay,
3.
thank you. 3, still just a number. So only differs by constant. Next, if y is equal to 3 to the minus x,
Okay.
y prime is equal to, not y inverse, y prime is equal to,
Negative 3 to the negative x times, yep, natural log of 3.
same thing as before, just make sure you do the chain rule and multiply by the derivative of this thing, which was negative 1. Make sense what I did? Okay, next one. If y is equal to sine of x, or 3 to sine of x, then y prime is equal to
3 times sine of x.
3 to the power of
2
sine of x.
Yeah, sine of x times cosine of x.
Times natural log of 3.
Don't forget your natural log of 3.
Okay.
Right? If 3 happened to be e, then you can forget natural log of e. Because natural log of e is 1, and so it doesn't change your answer.
Okay.
So always take the natural log of your base. When it's e, that comes out 1, and so that's why it seems like we're ignoring it in that case. Okay. Let's see. Note. Oh, we already made this note. Note that we can change our base. So we already said right at the beginning the derivative with respect to x of natural log of log base a of x with 1 to the x times log base a of e. If you do a change of base formula, then you get natural log of e over natural log of a. Natural log of e is just 1, so you get 1 over x times natural log of a. We already had that discussion over there.
Okay.
So no need to rehab it here. The only reason I'm rehashing it out here is because at this point in the book is when the author finally introduces log base a of x at the very end, which you'll notice that's what we started with. And so he asks you to calculate the derivative of one and then the integral of the other. So we'll do both. Alright, so if y is equal to log base 10 of 3 to the x, what does y prime equal?
1 over 3x plus 1
Okay.
times, oh, that's a log, times the log of 10 to the e,
Natural log.
Seeing that?
yeah,
Okay, what else?
and that's just equal to,
Alright, you're confusing me. Losing track of what you're doing.
Within
Let's
that.
just look at the formula. Log base a of x, when we take its derivative, is 1 over x times natural log of e over natural log of a.
Yeah.
What's natural log of e?
1.
1.
1. What's natural log of a?
10.
Natural log of 10.
Oh, natural log of 10.
Right?
Oh, I see.
Now, don't forget your chain rule. Times the derivative of the inside.
What?
What inside?
3?
3. Always and forever have a chain rule.
Okay.
Because remember, you could always write this as, you do the chain rule until it terminates. We're doing the integral with respect to x. So what's the derivative with respect to x? What's the derivative of 3x plus 1 with respect to x? It's 3 dx dx, which is 1. If there were a y there, then it would be 3y dx, which is why we do y primes.
Yeah.
So you're always doing chain rule, always and forever, until it terminates. Until you got a dx dx, and then you're done, because that's just 1.
Does the 3 cancel out?
No, nothing cancels. So we can rewrite this as 3 all over natural log of 10 times 3x plus 1. Nothing cancels.
Okay.
Natural log of 10, maybe put parentheses there, make sure we know. I'm not doing natural log of the whole thing. Okay, that's y prime. Now let's calculate our integral.
Okay.
So now we want the integral of log base 2 of x all over x dx. Now another thing that you can do, if looking for the how to use the rules directly is throwing you off and you want natural logs in there, just rewrite it with natural logs. You can always and forever rewrite with natural logs and never actually work with this log base 2.
Okay.
So log base 2 of x is equal to natural log of x over natural log of 2. That's our change of base formula.
Okay.
You with me?
Mm-hmm.
So I can rewrite this, if it's throwing you off, it's equal to, natural log of 2 is just a constant, so I'm going to pull 1 over natural log of 2 all the way out, times the integral of natural log of x over x dx.
Okay.
And if this is easier for your brain to consume than this is, do that. Make sense?
Mm-hmm.
Okay, now we need to pick one of those to be our u. What should we pick to be our u?
X. No.
Try again.
Natural log of x.
Smart choice. So now if we let u equal natural log of x, du equals what?
It's just 1 over x.
1 over x dx, so dx over x. But yeah. With me?
Okay.
So then our integral is equal to 1 over natural log of 2 times the integral of, what do we have? In our numerator, this dx and x cancel out, just giving you du, and then we have integral of natural log, and then integral of u. You see that?
Yeah.
No, where did you...
Natural log of x turns into u.
Yeah.
Dx over x turns into du.
Oh, I see.
Good?
Mm-hmm.
And now obviously we know how to calculate that integral. That's equal to the integral 1 over natural log of 2 times u squared over 2, right?
Mm-hmm.
Yeah.
So that's equal to, substitute back in our u's, what was u?
Natural log of x.
So this is equal to natural log of x squared, right?
Mm-hmm.
All over 2 times natural log of 2. Plus a constant.
Okay.
Let's look at that, make sure I didn't make a mistake. We did that. Natural log of x squared all over 2 times natural log of 2 plus c. Good. Okay, we did it right. So that finishes 7.2. Or 7.3, I mean.
7.3.
Mm-hmm. So we just did 7.2 and 7.3. 7.1 was inverse functions.
Yeah.
Yeah.
Okay,
What about the rest of 6?
we weren't doing the rest of 6, remember? The rest of 6 had to do with physics problems. So you were going to be calculating things like work. You don't know what that is. You were going to be solving physics problems.
Okay.
And I decided it'd be better to do more calculus and then go back and get the physics when we need it, as opposed, or do more calculus. It would be better to cover the physics in physics, because I don't like having to jump into the middle of physics just to do some applications with integrals. Okay, so our last section that we'll be covering is our section on differential equations. Differential equations, in particularly the types of differential equations we're going to be talking about, are called separable differential equations. It's like the simplest form of differential equations. Kind of like the simplest function to take a derivative of is like x to the n. It's like the easiest function to take a derivative of. Separable functions are like the easiest types of differential equations. The easiest ones to work with, the easiest ones to solve.
Okay.
What kind of functions?
Differential equations. Oh, they're called separable.
Separable?
Separable differential equations. So we're going to be looking at differential equations, and we're going to be looking at the simplest one, separable differential equations. Now, what is a differential equation? A differential equation is an equation whose derivative, dy with respect to t, is equal to or depends on the initial function.
That
Don't
doesn't
know.
make sense.
So y prime is equal to some constant times y. Notice how y shows up in the derivative.
Yeah.
When the function itself shows up in the derivative, then that's what we call a differential equation.
Okay.
You're saying it has to have the variable or the function?
the function, y. If y is some function f of t, then it shows up in its derivative.
What does that look like with real numbers?
So let's talk about a real-world example. Because now differential equations are what's used tomorrow in the real world, so we can talk about real-world phenomena to make sense out of all these. So let's say that you wanted to monitor population growth. You wanted to graph or predict future population growth. Right? Well, the change in population, what you call the change in population, what is that going to depend on? What are the factors that are going to determine how fast the population grows?
What it is right now?
Its current population size, which is y.
Okay.
And then there might be some other stuff, some constant.
Or
But notice how the change in population growth, how fast your population grows, depends on the current population.
Mm-hmm.
Does that make sense?
but y isn't your initial function.
If y is my function that gives me my current look, if y prime is my change in population, then y is my current population.
Okay.
Right?
Yeah.
And you're saying that y prime depends on y.
Mm-hmm.
Make sense?
I think so.
So if you were going out there on your own trying to come up with a function to model future population growth, whatever that, if you were trying to come up with a function that models a change in the population, so I say, Peter, I want you to come up with some function that will tell me the change in Centennial's population for any given year. That's your job.
Okay.
Or to come up with a function that gives me Centennial's population at any given year. If you're going to tell me Centennial's population any given year, you're going to need to know the change in Centennial's population.
Yeah.
And so you're going to have to come up with some sort of function to model that population.
Okay.
And differential equations are the equations that enable us to do that. So here's what you're going to know. First off, you're going to know that you want y to give you the population at some time t, where t is years into the future.
And it can be any year, right?
It can be any t, it can be plugged in.
Okay.
You know that y at 0, we're going to say y naught is the current population. You can check the current population right now and see what that is,
Mm-hmm.
right? So we're trying to figure out what y is at any future point. We know it's going to change with time. You know y at the current population. You know y right now. You can figure out the current population. And you know that the change in the population is going to be somehow proportional to the current population.
Okay.
If I have 1 billion people in Centennial, the population grows faster than if I just have 100 people in Centennial. Then the population grows slower. You with me?
Mm-hmm.
Okay. So now let's see all the information that dy dt gives us about this. If you know that it varies with the current population, so the way I'm going to rewrite this is I know that y prime is equal to k times y. I just wrote the same thing, right?
Yep.
Actually, no. We need to keep it dy dt, sorry. So we have dy dt is like this. I'm going to move my y over here and my t over here. So I'm going to get dy, maybe I'll write 1 over y, dy, is equal to k times dt.
Isn't it 1 over dt times?
dt goes up,
Oh, I see. We're fine.
y comes down. Now this is why it's called the separable differential equations. I was able to get all my y's on one side and all my t's on the other side. You can't always do that. This happens to be the case where you can. That's where separable comes from.
Okay.
It's just a name. All you'll be working with is separable differential equations, so you can just think about them all as differential equations for now. Anyways, okay, so I know that 1 over y dy is equal to k times dt. Now I can integrate both sides. You with me?
Yeah, but then you have to write k in terms of t, right?
K is just constant.
Oh.
Okay, so what's the integral of 1 over y dy?
It's the natural log of y.
Natural log of y is equal to, what's the integral of a constant?
Just a constant.
Times t. The integral of a constant with respect to t is that constant times t,
Oh, yep.
right?
Mm-hmm.
And then we have plus some constant that we don't know.
Okay.
You with me?
Yeah.
Okay. So then, raise both sides to the power of, do e to this power and e to this power. So e to the natural log of y is equal to e to the kt plus c.
Okay.
You with me?
Yeah.
Now e to the natural log of y is the same thing as, come on,
Just why?
just y, so this is just y, is equal to e to the k times t plus c. You with me?
Yeah.
Now, e to the k times t plus c is the same thing as e to the k times e to the c.
Yeah.
You with me?
No.
Because of the.
E to the k plus c
Plus C. Yep.
is the same thing as e to the kt times e to the c. You with me?
Yeah.
Now I'm just going to write that e to the c up front. You with me?
Okay.
So here's what y equals. We just figured out our equation for y. This is y at some time t. Y at t is equal to e to the c times e to the k times t, right? But we don't know what c is,
Yeah, it can be any constant.
because it's just some constant. And in fact, e to the c is also just some constant, right?
Yeah.
So I'm just going to call this whole constant a. And we need to figure out what a is.
Okay.
What do I get if I plug in 0 for t?
You get
Just
A.
You just get a. And what do we mean by y at t? That means what's the population at time t? What do we get?
You get A.
You get a. So a is just our initial population, which we called y naught.
oh, okay.
So y at t is equal to y naught times e to the k times t. Here's your equation for population growth. And depending on how fast your population grows, changes the k. Notice that we still don't know exactly what this k is, because not all populations grow at the same rate. We're talking about population of people, or are we talking about population of rabbits, or are we talking about population of bacteria?
So what?
Those
is
all reproduce at drastically different rates.
your K? So what is your K? You're
It's
saying-
some constant. It depends on the actual population that you're talking about. You have to figure out from your population what the k is.
So for Centennial, what would that be?
We would need to know Centennial's population now and Centennial's population at some other time, and then calculate the k based off of that. So we'll do somewhere we actually calculate the k.
Okay.
I just wanted to give you big picture motivation. How might we come up with some equation to model population? And the equation that we came up with is, if this is true, if y some function t, y naught is equal to f of 0, and dy dt is equal to that, then we found out that y is equal to y naught times e to the k times t. Where that k and that k are the same k, you still need to figure out what that k is, and that k will depend on your population.
Okay.
Gotcha.
So now, that's the great big intuition for this whole section. So now we just solve a bunch of problems over and over again using this type of thinking. Most of them are going to be more real-world type problems, but they're going to give us some problems that aren't really real-world type problems just to make sure we understand it.
Okay.
So they say, solve the differential equation. So here's what this information we'll use in general. Now we're just going to solve a differential equation. Let me try and get my laptop closer. So just to solve the differential equation where we know that dy dx or dt dx is equal to 1 plus y times e to the x. It says where y is greater than -1. Okay, so this one we're just solving the differential equations. We'll see where this information is more useful when we get story problems.
Okay.
Okay, when you have a differential equation, you're always going to get a separable differential equation, which means you can get all your y's on one side and all your x's on the other side.
Okay.
So get all my y terms over here, all my x terms over here. So this is going to be the same thing as 1 over 1 plus y dy is equal to e to the x dx. You follow me there?
Yep.
Integrate both sides. Over here we get natural log of 1 plus y is equal to e to the x
Okay.
plus a constant. Right?
What about the constant on?
You just move it over here and it's just constant.
Okay.
So it's always just constant. And then you can solve that for y if we want to. The author just leaves it at that.
Don't you want to put it all to e?
You could put it all to e and then get 1 plus y is equal to all that to e and then move the 1 to the other side and get y equals that. And you could.
Okay.
But that's not a terrible way to have it written. And that's where the author leaves it. Alright. Let's do another one. If I know that dy dx is equal to y times x plus 1 dy dx. Okay, so a little bit more complicated. Y times x plus 1 times dy dx is equal to x times y squared plus 1. Like that. Good? Same exact trick. Move all your x terms to one side and all your y's to the other. So on the y side over here, we're going to get y over y squared plus 1 dy is equal to, on the x's over here, we're going to get x over x plus 1 dx.
Okay.
You with me?
Yep.
And now we need to integrate both sides of this thing.
Okay.
So then the integral of this is equal to the integral of this. We'll calculate each of these integrals separately. What does this integral equal?
Just y times.
Well, just plug in, do your u substitution real quick.
Oh.
So over here, maybe we'll just solve this one down here. So the integral of y over y squared plus 1 dy is equal to, let's do our u substitution. If u is equal to y squared plus 1, du is going to equal 2y times dy, right?
Mm-hmm.
So this is going to equal, in terms of u, we're going to get, let's see, 2y dy gives me my du. So we need a 2 in the top, so we have to take a 2 out of the bottom as well. So 1/2.
You lost me.
Okay. I'll write it out. Just multiply top and bottom by 2.
With the u in there.
There's no u in there yet. Everything's a y. I took this and I multiplied it top and bottom by 2. That's it.
Okay.
Yeah.
Nothing more.
Why did you take out the 1/2?
I could have left it in there, but I'm going to pull it out anyways.
Okay.
So 2y dy, that's du. Y squared plus 1, that's u.
Oh, I see.
Which is equal to 1/2 natural log of u plus some constant, but we'll take care of that in the end. So that's what this one equals, right?
Yeah.
Mm-hmm.
That is just dying slowly but surely. Let's try our next one. So for our next one, we're looking for the integral of, rather than writing x over x plus 1, I'm going to split this into 2 fractions. So I'm going to write it as, oh no, I can't, sorry. We can't do that. Let's see. I'm kind of going to do it. I'm going to do u substitution first. I'm going to let u equal x plus 1. You with me?
Yep.
Du is still just equal to dx.
Okay.
And so this is going to be the integral of x now becomes u minus 1
Yeah.
all over u du. You with me?
Yeah.
Now I'm going to split this up as two fractions. So thus the integral of u over u is just 1, minus 1 over u is just 1 over u du.
Okay.
With me?
Mm-hmm.
Now we integrate, and what do we get? What's the integral of 1?
Just integral of constant is constant.
No.
0. No, it's x. I mean u.
U! There we go. U minus what?
Natural, yeah.
Natural log of u. Going back to our x's, we get x plus 1 minus natural log of
X plus 1.
x plus 1. Good?
Okay.
Yeah. Plus c.
Okay. Another way I could have done that is, well, that's probably more intuitive to the way you guys would have done it. I could have also done x plus 1 and minus 1 at the top, and then split this into two fractions. That's the way I normally want to do it. Let me just show you that way as well, because it's a faster way without the u substitution, and it's a common trick to do. So this would also be equal to the integral of x plus 1 minus 1 all over x plus 1, right?
Okay.
Now I can write that as x plus 1 over x plus 1 minus 1 over x plus 1.
Yeah.
So x plus 1 over x plus 1 is still just 1. Minus 1 over x plus 1.
Oh, I see.
With respect to x. And then we still get an x minus natural log of x plus 1. Now what did I do wrong? Because that's not the same thing. Did I do something weird in my substitution here?
Seems like you did right to me.
Oh, they differ by a constant. Plus 1 is just a constant, because this is really plus c1, and this is really plus c2. And c2 is equal to c1 plus 1, because plus 1 is still just a constant.
I see.
So when we ignore the constants, it comes out to just x minus natural log of x plus 1.
Okay.
You with me?
Mm-hmm.
Okay, so altogether, when we take both these integrals, and we know that they're equal to each other, we found out that, what was the answer to this one? I found out that 1/2 natural log of y squared plus 1 is equal to x minus natural log of x plus 1 plus a constant. Putting all our constants together in one giant constant.
Okay.
Good? And that's probably how he leaves it, to be honest. One half natural log of 1 plus y squared is equal to x minus natural log of x plus 1 plus c. Okay. Now, more realistic type problems that we'll be solving with these separable differential equations will be things like population growth, more story type problems.
Okay.
You know, like when you're supposed to calculate the volume of, or not volume, when they give you problems like, what are the dimensions of a can to minimize its volume if it has to have this much volume?
Mm-hmm.
Or minimize the surface area if it has to have more problems like that. More real world problems, you know? Okay, the biomass of a yeast culture in an experiment is initially 29 grams. So we initially have 29 grams of yeast. That's like its current population.
Okay.
So we know initially we have 29 grams of yeast. That's like the current population. This yeast is going to be growing. After 30 minutes, so our t is going to be in terms of minutes, but so now I know y naught, or y at 0 is at, y at 30 is equal to, after 30 minutes, then we have 37 grams. 37 grams.
Okay.
Assuming that the equation for unlimited population growth gives a good model for growth. This is the equation for unlimited population growth, that's what we mean. Because this doesn't take into any external factors like Centennial only has so much area. obviously 200 billion people can't live in Centennial.
Yeah.
There's a natural cap. Same with if I'm growing a yeast culture, eventually it reaches the borders of the yeast, or there's only so much of what the lab's feeding the yeast to actually grow on. So it will grow and grow and grow, but there will eventually be natural limiting factors. So we're saying, assuming that we're not coming close to our natural limiting factors.
Okay.
Growth of the yeast. How long will it take for the mass to double from its initial value? Okay, so we're trying to find how many minutes will it take for us to have 58 grams of yeast.
Okay.
You know, after 30 minutes, we're going to have 37 grams. I need to come back into the lab when there's exactly 58 grams. So when do I need to be back in the lab? Something like that. Okay, so let's figure this out. So I know that my yeast population is equal to 29, my initial yeast population, times e to the kt.
Okay.
And this is y at some time t. You with me?
Mm-hmm.
Just using information we already gathered when we derived this equation. Good? Okay, so now I know that when y is equal to 30, sorry, when t is equal to 30, my y is 37. So I know I have 37 grams at 29 times e to the k times 30. You with me?
Yeah.
So now notice that I can use this information to solve for k.
Okay.
And that's why I meant when you said, how would we figure it out for Centennial? I said we need to know their population at another time. So since we know the initial population and the population at another time, we're able to figure out the whole equation.
Okay.
Okay, so now we got to figure out what that t is, or what that k is. So first off, I'm going to put my e term over here, just because it seems more natural to me. So this is e to the 30k is equal to 37 over 29.
Yeah.
Good? So now take the natural log of both sides, and I get 30 times k is equal to natural log of 37 divided by 29, or natural log of 37 minus natural log of 29. However we want to write it.
Oh yeah.
So then I get k is equal to, I'll put it together as a whole, well, that's a lot of fraction. I have enough vertical space. K is equal to, put those back together as a fraction, natural log of 37 over 29 divided by 3. And now you can plug that into your calculator.
Divided by 30, right?
30, thank you, 30. And then you can plug that into your calculator and it will give you a number. And that number will be 0.008118.
That's cool.
That's your k.
Oh, so now you know.
So now you know for any time in the future,
Yeah.
right? So now I know my equation is y is equal to 29e to this k. I'm not going to write out that number. I'll keep using k. We know what k is, just for the sake of shorthand. But now we know exactly what that k is.
Mm-hmm.
And this will tell us our culture, how many grams we'll have at any time.
Okay.
Okay, the last part of the problem was to figure out at what time will we have double this, or in other words, at what time will we have 58. So I want to know when will we have 58 equal to 29 e to the k times t,
Okay.
right?
Okay.
Now, once again, I'm just going to start rewriting up here. I know e to the kt then is going to be equal to 1/2, or 2 I mean. No,
No, 1/2.
2. 2.
2.
Yeah, 58 divided by 29. When is it equal to double?
2.
Look,
Oh,
the general way I'm solving is I'm solving when is y naught e to the kt equal to 2 times y naught? When do I have double? Divide both sides by y naught. That's the same thing as saying when is e to the kt equal to 2?
Okay.
You see that?
Mm-hmm.
Okay, so when's e to the kt equal to 2? Well, that's when k times t is equal to natural log of 2, or that's when t is equal to natural log of 2 divided by k. Again, that's just a number. That's just a number. You can plug those numbers into your calculator. Strongly recommend, if you don't have one, you get a graphing calculator because it has features to store a number in a variable. so you can actually store it in your variable k and then just plug k into your calculator as normal.
Okay.
And when you plug all that in, you'll get roughly 85.38
Minutes, right?
minutes. 85.38 minutes. So come back in roughly 85 minutes and you should be good.
Okay. It's kind of cool.
It's very cool.
So you can.
And we'll do
actually-
much cooler stuff than that. You know, you're getting a little bit of taste for physics here now. So next one we're going to do is, we'll come back to the disease one if we have time. That was not as cool.
Does that formula work? Like your unlimited population growth formula? Does that actually work?
Yeah, it's a good model. In cases, you can always break the model. And when you go take a class called Differential Equations, you'll learn how to better model and better model. And how you can take into account things like, I want to model rabbit population growth, but remember, as rabbit population goes up, so does local fox population, and the more foxes there are, the more rabbits they kill. So the rabbit population goes up, which causes the fox population to go up, which causes the rabbit population to go down, which causes the fox population to go down, which causes the rabbit population to go up. And so it gets quite complicated, but yes, everything we do in physics, we use differential equations to model. All of them. Differential equations describe our universe, for whatever reason. Talk about Maxwell's field equations for describing law of electricity and magnetism, differential equations. Einstein's field equations for describing gravity, differential equations. Show up left and right. Okay, number 5. So now we're going to talk about radioactive decay. And it'll give you a sense of the idea of it. This is how we date things, and you've probably heard about a half-life.
This is like carbon dating?
Carbon dating. That's exactly what we're going to talk about. Carbon dating. What is carbon dating?
Okay.
So you inside of you, you're mostly, all life on planet Earth is made up of carbon atoms.
Yeah.
And living life happens to have a certain proportion of a particular type of atom called carbon-14. So as long as you're alive, roughly, I'm just making up numbers here, but roughly 1% of the carbon atoms that make you up is carbon-14.
Okay.
Special type of carbon atom. This special type of carbon atom is a radioactive carbon atom. It decays. Which means after some amount of time, some unknown amount of time, it splits and it's no longer carbon. And the fact that this happens is what enables us to do carbon dating.
Okay.
So rather than modeling population growth, we're going to model how carbon-14 decays inside of you. So you have a bunch of carbon inside of you, carbon-14 inside of you that starts decaying. So you might kill you now when you start decaying.
Okay.
Then your carbon-14 population inside of you is going to start dying off, dying off, dying off. And how long it takes for half your population to die off, we call the half-life of that atom.
Okay.
So if you had 100 carbon-14 atoms, and you timed how long it took for there to only be 50 carbon-14 atoms, so the other 50 decayed, then we call that its half-life. How long it took for half the population to go away. Make sense?
Yeah.
Okay, so let's actually get into the equation that we use. So we're still using the same equation. We're going to use y is equal to y naught times e to the kt. Still the same equation.
Okay.
Now our constant is going to come out negative because the function is now going to be decreasing. We're talking about the k rather than the population growing. So your book shows a minus k there, so that the actual k constant can stay positive. But it doesn't matter if you use a k or a minus k, it's just going to make, so that when you calculate k, it's either positive or negative.
Okay.
Doesn't matter. Make sense?
Yeah.
So I just want to show you that because in case you look in your book for how to solve a particular problem and you see that, I don't want you to be confused. So the decay of radioactive elements can sometimes be used to date events from the Earth's past. In a living organism, the ratio of radioactive carbon, namely carbon-14, to ordinary carbon stays fairly constant during the lifetime of an organism, being approximately equal to the ratio in the organism's atmosphere at the time that they died, or while they're alive. After the organism's death, however, no new carbon-14 is ingested, and the proportion of carbon-14 in the organism remains in the organism's remains decreases as the carbon-14 decays. So the amount of carbon-14 in me right now is roughly the same as the carbon-14 in the atmosphere. When I die, no more carbon-14 gets into me. The carbon-14 inside of me starts decaying.
Yeah.
And so that's how we figure out how long ago I died. Scientists who do carbon-14 dating often use a figure of 5,730 years for its half-life. Find the age of a sample in which 10% of the radioactive nuclei originally present have decayed. 10% have decayed, so we have 90%. Okay. So here's what the half-life means. So this is just a matter of experiment. I know, well, y equals y naught. Here's what it is. I know that I have half of what I initially had.
Okay.
When we plug in years, 5,730. You with me? That was an experimental fact. Someone sat there in the lab forever counting. It's not really how they did it, but it's a given number. Here's a half-life that someone in the lab calculated for us. Here's a half-life.
Okay.
Which means after that many years, we have exactly half of what we start with. Oops, I forgot my y naught. Why do you guys let me forget my y naught? Divisible size by y naught, in other words, 1/2 is equal to e to the negative k times 5,730.
Okay.
You with me?
Mm-hmm.
Or in other words, take the natural log of both sides. You with me?
Yeah.
And I'm going to write this side first. So negative k times 5, I'm going to write the k last. Negative 5,730 times k is equal to natural log of 1/2.
All right.
Okay.
Which gives me that k is equal to natural log of 1/2 divided by minus 5,730. You with me?
Mm-hmm.
Okay. So when you throw that into your calculator, then you get k is roughly, where are you? (1.2 times 10 to the negative 4). 1.2. Are you guys used to scientific notation?
Scientific notation.
That's what that's called. Okay. This is the same thing as 0.00012.
Okay.
It's this number. Now shift the decimal place to the left 4 times.
Yeah, you do
So
this in
1,
chemistry all
2,
the time.
3, 4. Okay, so that number and that number are the same number.
Yeah.
Okay.
Okay. Now,
Isn't it negative though?
no, it's positive. Because natural log of any number less than 1 is going to be negative. We went over that explanation. Remember that natural log function is negative to the
That's
left of
right.
1. So a negative over negative makes it positive. That's why they arbitrarily threw a negative in it, the equation right there. So like k would always be a positive number. If you didn't throw that, yeah, k would have been a negative number. Doesn't really matter. It's just a constant. For some reason, they want to keep it positive. Anyways, so there's k. So now, what were we asked to do? We were asked to figure out how long it would take for 10% of my carbon-14 to decay.
So not 50%?
Not 50%, 10%.
Okay.
How long would it take to lose just 10% of that now? Now, you might be tempted, if it takes 5,730 years to lose 50%, and you only want to lose 10%, then it's going to be 1/5 of that.
Yeah.
Right?
That makes sense.
Might stand to hold. So we might say it should be roughly 5,730 over 5-ish. And we'll see how terribly off that is. Okay, so we want to know when we have only 90% of what we started with. I want to know when I have 0.9 of what I started with.
Mm-hmm.
So I'm looking for the t that makes this equation true. You with me?
Yeah, just that number up there doesn't make sense for finding 90%.
For losing 10%,
That's for losing 10%. Okay.
which is you still have 90%. Same thing. So this is, we've lost 10%. When will we have lost 10% or we only have 90% remaining?
Okay.
Same question. Good? So that's the same thing as when 0.9, I'm just going to write as 9/10. When 9/10 is equal to, divide both sides by y naught, e to the minus k times t.
Okay.
With me?
Mm-hmm.
Once again, take natural logs of both sides. I'm going to write this term first. That's the same thing as negative k times t equal to natural log of 9/10. Or that's when t is equal to natural log of 9/10 over negative k. Notice this will be a negative number. This will be a negative number. Positive together gives us positive years. And if you go plug that into your calculator, what do you get? You get roughly 871. Notice how we were calculating this way. It gives us well over 1,000.
Yeah, it does. Okay.
So, there we go. That's how long it would take you to lose half your carbon-14 atoms if I killed you right now. Or if Peter killed you. Doesn't have to be me. Or you had a heart attack. Whatever. And so this is how we can date. We work it kind of reverse from what we just did here. Well, no, this is exactly how we came across it. So let's ask the question a little bit differently. Imagine you dig up some mummy, some fossil, some human remains, and you notice that it only has 0.9% of the carbon-14 atoms that it should. It only has 90% of the carbon atoms that it should.
Okay.
And you say, so when did this person die? Roughly 871 years ago.
That makes sense.
Or if they only had half of them, then we said, oh, they died roughly 5,730 years ago. That's how we can date things. And we can date much better things than that. That's how we go and we get a dinosaur bone fossil, and we can carbon date that and see roughly how long ago that dinosaur lived. So that's how carbon dating works.
Okay.
Pretty cool, right?
Yeah.
Now the coolest one, what's it called? It's like Newton's heat law or something like that. But this is actually used in forensics when they are solving murder cases. When you're solving a murder case, a common question is, when did that person die? And if I come across a dead body in a room, and I know the temperature of the body, I can tell you how long ago that person died.
Really?
Assuming that the temperature in the room stayed constant. Yes. You can determine how long ago someone actually died.
How
What
long
the heck?
can you do that before it becomes an
It dies off the more time that goes by. Obviously, it doesn't work over 10 years,
Yeah.
but it does work over 10 hours, assuming the room stayed constant.
Even if it was in like a freezer or something, as long as it was constant?
As long as it was constant. Doesn't matter what the temperature would have been. Correct.
Interesting.
Over a certain amount of period of time.
Yeah.
There comes a point where it gets so close to the bottoming out point that you can't tell anymore. As long as it's still warm enough that you can detect the difference between it and its surroundings, then you can get a pretty good approximation. Okay, so Newton's law of cooling is what we call it. Newton's law of cooling. And when we calculate the change in the heat with respect to time, what do we expect the change to depend on? First off, there's going to be some constant. It's cooling, so we're going to use a negative k rather than a positive k.
That makes sense.
Just because cooling, so we're going to expect numbers to get lower and we want the k itself to actually stay positive. But when my soup is cooling down, what do we expect the temperature, how fast the temperature of the soup is changing to depend on?
Temperature started as?
Its current temperature.
Yeah.
So we want to know how fast it's changing right now. Notice if my soup is the same temperature as the room around it, the temperature stops changing.
Yeah.
So it depends on its actual current temperature, its actual H.
And the
air
difference
around
of
it.
the temperatures, right?
The difference of the temperatures, that is exactly right. And the S for, I can't remember what the S typically stands for. S for environment somehow. There's some way to think about S as the environment. Surroundings. We'll stick with that. Surroundings. So the bigger the difference between the current temperature and the temperature of the surroundings, the more there's a change in the temperature per second. Right?
Yeah.
If I take really hot soup and I take it into a really cold freezer, the temperature is going to change a lot faster than if I take soup that's 81 degrees Celsius and bring it into a room that's 80 degrees Celsius. Makes intuitive sense? And obviously, if I take 80 degree soup in a room that has 80 degrees Celsius, there's no change. The change is so small, it's 0.
Yeah.
Roughly. There's always little weird stuff going on. Okay. So, if we let y equal h minus h sub s, if we let y be the difference, then the derivative of y with respect to t is then equal to, what's the derivative of h with respect to t? That's just the derivative of h with respect to t, whatever it is, I don't know.
Okay.
Minus, what's the derivative of a constant? Because notice, the temperature of your surrounding doesn't change. It's just the soup that changes.
That's 0.
So that's just 0. Or in other words, dy dt is equal to dh dt. Or in other words, if we let y equal h minus a constant, the minus constant doesn't change anything
I see.
in the derivative. So this is equal to that, which is still equal to negative k times, now we can replace the h minus h sub s with just y. Y is equal to h minus h sub s.
Yeah.
H sub s.
I see. Okay.
Follow that? Okay. So now we know that the solution dy dt is equal to that. So that gives us our equation that, once again, we have y dt is equal to that. So when you solve it, you get y is equal to y naught times e to the minus kt, same equation that we had before. If we substitute back out the y's for our h, then it's going to be h minus h sub s is equal to h at time 0 minus h sub s times e to the minus kt. I don't really care which equation we use, I'm just wondering which one the books can have you use. Okay, that's the equation the books can have you use, so we'll stick with that one. But you understand what all these are, right?
Yeah.
And you see how this, all we did is, we started with h's, we got it in terms of y's really quick, so that I could go from this step to this step without showing any work, and then put the h's back in.
Yeah.
Because you already knew how this being equal to this gives me this equal to this.
Yep.
So that was the point of the y's. Just to quickly show you how this leads to this. So ignore all the bit of work, this is, we were just working up to, here's our equation that we care about. Our differential equation.
Gotcha.
Good? Okay, so now, let's actually solve the problem that he gives us. A hard-boiled egg, should we frame this as a murder mystery?
Why not?
Okay, a person dies at 98 degrees Celsius, so that's really hot temperature, body temperature.
Yeah.
Now we'll come back and just do one afterwards. So a hard-boiled egg at 98 degrees Celsius is put into a sink of 18 degrees Celsius water. So you boil your egg, take it out, and it is 98 degrees Celsius. So our initial temperature of our egg is 98 degrees Celsius.
Okay.
Then we stick it into water. Water, that's our surrounding. We expect the temperature of the water not to really change that much as we put the egg in there. And so the temperature of the water is 18 degrees Celsius.
Okay.
Everything so far?
Yep.
After 5 minutes, the egg's temperature is 38. After 5 minutes, the egg's temperature is 38.
So time
Okay.
equal.
So, we have 38 here, minus, what's h sub s? 18,
Yeah.
is equal to, what was h sub naught? 98
Minus
minus
18.
18 times e to the minus k times how long? 5 minutes.
Yep.
So we're going to use this equation now to solve for k, and then once we have our k, they're going to ask us what's the temperature of the egg at some time, and then we'll be able to plug that in. So, but now we have enough information to figure out what our k is, right?
Yeah.
Yep.
So 38 minus 18 is equal to
20.
20 is equal to,
80.
I don't know, Oh, 80. What was I thinking? E to the minus k times 5.
Okay.
Just testing you. Okay, so divide both sides by 80, and we get e to the negative 5k, just going to write this a little bit different, is equal to 1/4.
Yeah.
You good with what I did there?
Yep.
Natural log of both sides. And now k is equal to natural log of 1/4 over minus 5, which is approximately, we'll get that from the book. But notice, negative, negative, it's going to come out positive.
Yep.
Okay.
And it comes out, roughly 0.28. Not bad. 0.28. Okay. Now, next, the x temperature at time t is that. Now find t. Okay, so our next job is to figure out how long will it take the egg to be 20 degrees Celsius. Maybe this is a habit of yours. You know that you can't stand eating the egg until it cools down to 20 degrees Celsius. You want to know, how long do I gotta wait to eat my egg?
Okay.
So, we want to know what's the t for when 20 minus 18 is equal to 98 minus 18 is still the same thing. That one doesn't change. 80 times e to the negative 0.28 times t. Right?
Yeah.
Okay.
So I want to know when 20 minus 2 is
20 minus 18 is 2.
20 minus 18 is 2. Divided by 80 is 1/40th.
Okay.
Unless I'm still broken. Minus 0.28 t. So, using that, we know that negative 0.28 t is equal to natural log of 1/40, right?
Yep.
Or in other words, t is equal to that over negative, now I forgot the number, 0.28.
Yeah.
Which comes out to roughly, whatever it comes out to, 13.
13.
Yeah, so you gotta wait roughly 13 minutes
That's right.
to enjoy your egg.
Well, at least he gets that 20 degrees Celsius.
Yeah, there we go. So how would you do this for trying to figure out when someone died? It's almost identical.
Okay.
Hold up. Why do you do 20 minus 18? I know, but aren't you trying to eat it at 20?
Yeah, H is the temperature of the egg. H is the temperature of the egg. H sub s is the temperature of the surrounding.
I'm still a little lost with that.
H was always just the temperature of the actual object in question.
Yeah, I got that. And your surrounding environment is the same.
It's the same always. So I want to know what time can I plug in here to make H equal to 20. If you're getting thrown off by this, let me rewrite it like this. It's equal to H times this whole thing minus H sub s over here. Pick a T, plug it in, spits out H.
Okay?
Where's that minus h?
It's plus H sub
Oh,
s.
plus H. Thank you.
Was it 1 over h sub s?
No.
No. We had
Oh,
H
yeah.
minus H sub s here, plus H sub s to both sides, and you get there.
Okay, I see it now.
Okay, so how would you do this for someone dying? The instant somebody dies, you always know that that is, what's the temperature when you die?
98
98.1 degrees Fahrenheit this time, not Celsius.
Yeah.
So we'll pretend it's just 98. So we know that in our case, H naught would equal 98, right, for your initial temperature. And let's say that you die, someone kills you out in the freezing cold, so they kill you outside where it is 20 degrees Fahrenheit, so below freezing. This time we're in terms of Fahrenheit, not Celsius.
Yeah.
And so if I come across your body, oh, not 20 degrees, let's say 18 degrees Fahrenheit.
Okay.
And so I'm just trying to make it follow the exact same problem we just did.
Yeah.
That's what I'm trying to do. And re-say it in a more...
They throw you in the freezer.
Yeah, and so if I wanted to know... So if I come across your body and I find out that your body has a temperature of roughly 20 degrees Celsius, 20 degrees Fahrenheit,
Okay.
then I can say, uh-oh, he's been dead for about 13 minutes.
Minutes?
Well, that was not quite right. We'd have to figure out a new K for the human body. And they already know the K for the human body, so that's going to be some given number. So actually, this doesn't work. Because I need one more piece of information. I need to know the temperature of a human body that's been dead for some amount of time.
Yeah.
And maybe if the internet's back up and running, we can Google temperature of a human body after, well, it also depends on the environment, so shoot, we can't do this until it gives us one. But you see how in practice you could do it
Yeah.
if you already had this information collected.
Okay.
So if you could already figure out what this K is for the human body, if that's something that someone already figured out for you, then now you could figure
happen
out,
to run across a dead body.
and you happen to cross a dead body, yeah, they do it all the time. Because that's how you can try to nail down victims. You can try and say, where were you 3 hours ago, because you know that's when she died, versus where were you 2 days ago, because you know that's when she died. And so getting a rough time on when that person actually died is very important in forensics.
Yeah, that makes sense.
So that's common one. And you can use it for also calculating all sorts of things in physics, heat cooling down. One of the first estimates of the life of the Earth was calculated roughly using this equation, because he calculated roughly how much energy, I don't know how he got his initial estimates on how hot the Earth would have been to begin with, but he said the Earth started out such and such hot, and he calculated how much heat the Earth is radiating away, and from that was able to figure out these equations and came up with the first calculation for the age of the Earth, which was something like 10,000 years, something really short. Because it doesn't take into account the fact that inside of the Earth we have activity producing new heat. He thought it was just a hot object cooling down, going way, way back for the first times that calculations of the age of the Earth were made.
That makes sense.
But here's how they tried to do it. They said, here's how fast the Earth should be cooling down. We have our rough estimate on what its initial temperature was. We know what its current temperature is. Therefore, here's how old the Earth should be roughly. It's cool. And it turns out it's a terrible guess, but cool idea.
Yeah.
But you can do this for a lot of other things. If I stick an ice cube in water,
Yeah.
actually, stick an ice cube in water, yeah, that goes through two phases. Because you got the ice cube cooling down and then actually melting. We don't get to talk about phase change yet. That's chapter 20 in our physics book. We'll get there.
Chapter 20.
Might not be that late. I think chapter 20 is actually entropy, so it's going to be like chapter 19, chapter 18.
Oh, we're going through chapters a lot faster, that's right.
Yes, much faster chapters. Anyways, that's the end of physics.
Calculus?
Calculus. That's the end of calculus. We covered all of Cap 1, so we'll do your tests, and then we'll start physics.
Sweet.
Stoked.
Is our final going to be on everything?
I haven't decided yet. I won't know until I make it.
Okay.
So then
But let's actually really quick go over your guys' last test. Forgot we needed that.